My dear NEET warriors, welcome to the Zero to Hero series. And I hope you guys are ready to gain your 40 marks for your NEET 2025 examination. The entire of modern physics, which includes photons, dual nature, photoelectric effect, also your atoms, structure, atomic structure, spectra, nuclear theory, and also your semiconductors and electronic devices. The entire unit, guys, heavy weightage unit. So let's begin with the Zero to Hero series targeting 650 plus score. If you are a student who feels that I have not done enough and needs that final push, this is the series, the ultimate series that you have been looking for. And let's begin with a bang. Welcome, Atluru, Kirti, Pratibha, Jain. Welcome, Pavitra. Hi, Bharati. Nice to see all of you. Hello, Advika. Pandu is also back. Oh my God. Hello, Yalini. Nice to see you. Hi, Vaishnavi. Good evening. Good evening. All right, very cool, very cool. Good evening, guys. So let's begin with the class, and also let me remind you that if you have not yet subscribed to the channel, please subscribe so that you get all the important updates and notifications along with the academic classes. Also, we have already kickstarted the Zero to Hero series, so make sure that you are watching all the sessions live. Yep, and also smash that like button down there in case you have forgotten to do so. And we are coming in Bengaluru, so please fill this form. So all the students in Bengaluru, please fill this form. We'll come to other cities also, but just wait for it. Just give us a couple of days. We'll plan out the entire April month. Okay, great. So let's begin with the class. And some of you might be interested in the regular batches or crash courses. That link also I have put over here. The crash courses start at 1,999 rupees. Okay, and you have other batches also with combination, like you get flashcards and all India level test series. So you can check out all the options down there. So let's begin with the class, and I hope you guys have smashed that like button down there. Welcome. Good evening, Loyola. Hi, Krishna. Hi, Bunty. Hi, Navina. Not lots of new names. Nice to see you guys all. So let's begin. The first part of this is basically your photoelectric effect and Einstein's equation. So let's understand all these things properly theory wise, and then we can slowly proceed ahead. See, light can be used to emit electrons from a metal surface. This phenomena where light falls on a metal surface to emit electrons is called photoelectric effect. And now there are actually multiple ways to emit electrons from any surface. So emit to emit electrons from a, let's say, metallic surface, there are multiple ways. First one is thermionic emission. The second one is called field emission. The third one is called photoelectric effect or photoelectric emission. What are the three different techniques? Imagine you have a metallic surface. You heat it. Okay, imagine you have some metallic surface and from below you provide some heat. What will happen because of the heat? These atoms begin to vibrate. Duck, 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 duck. They will start colliding with each other. Once they start to collide, what will happen? There are electrons revolving. So when these electrons collide, they will get knocked off and they will come out. So you will see that once you heat this particular metal, then you will see electrons coming out of it because of the thermal energy and the collisions. That is thermionic emission. What is field emission? Imagine you have a metallic plate over here and here, something like the plates of a capacitor. One is connected to the negative side, one is connected to the positive side. Obviously, there will be a very strong electric field if you apply a strong voltage. Now, imagine you increase the voltage difference. If you increase the voltage difference and you make it very, very high. So what will happen then? You will see there will be a very, very strong field over here, a strong electric field, a strong electric field over here. This strong electric field will force the electrons from these plates to come out. So these electrons will be ejected out of the plate and they will go bang onto the other side. The best example of this is lightning. Lightning is like a field emission where there is a very high voltage between the clouds and the ground surface, and this high voltage produces high electric field. This high electric field applies a very strong electric force. So the electrons which are free enough can be plucked out from their atoms. They will be forced to be they will be forced to come out of that atom, and that's how the electrons are ejected. That is the second way. The third one is photoelectric emission, where again you have, let's say, a metallic surface, and now this time you have light falling onto it. Basically you have light falling onto it, and this light energy gets used up in emitting these electrons. That is called as photoelectric effect. Are these three things clear? Let me know quickly in the chat box. Thank you so much, Piyush. Okay. Princess, the series will go until around April 10th, April 15th, around that time. So around 2 to 3 weeks, we'll try to complete all the high weightage chapters. And in between, there is another thing which is also coming up for PYQs, like I mentioned in yesterday's lecture. Okay. Yeah. Pandu, of course, how can I forget you? Yes, our Pandu is back. I know Pandu also comes out with another account, I think Champa. And I'm so glad, Pandu, you are back. Okay, clear. Now, we are specifically going to focus on the photoelectric effect. See, if you talk about light, it has dual nature, and we'll talk about the dual nature later on. But the particle of light, the particle of light is called as a photon. The particle of light is basically called as a photon. Now, this photon has certain properties which we will talk about, obviously. So, the energy of a photon, that is also the quanta of energy. Basically, whenever energy comes from light, you turn on the tube light, you think continuously zoop, 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 light is throwing energy at you. Actually, it feels continuous, but at a small level, it's all in small, small packets. Imagine somebody takes a water pipe during Holi or something, and they splash water using that pipe. So water is coming continuously. Second option, somebody takes that same pipe and they fill water balloons, and then they throw on a person. Again, fill a water balloon, throw at a person. Again, fill a water balloon, and then throw at a person. So light travels like these water balloons. So the energy is stored in packets, which is called quanta, and these quanta of energies keep coming towards you. Each quanta, that water balloon which is being thrown at you, like photons, they are basically exactly the behavior of photons. Okay, so light energy does not come continuously, it comes in the form of bursts, like packets, small, small packets of energy. Each packet is called quanta. That energy is of the photon, which is given by Planck's constant into f, which is frequency, which we can also write it as h into speed of light divided by lambda. We all know what's the value of h. H is your Planck's constant, which is your Planck constant. The Planck constant, which is having a value of 6.62 into 10 to the power minus 34. Okay, this is your speed of light. This is your speed of your light given by 3 into 10 to the power 8 meters per second. This also can be further converted in electron volt unit. In electron volt unit, it is better you remember it. 1240 divided by lambda, provided this lambda is in nanometers, then the answer that you will get is in electron volt. The answer that you will get is in electron volt. How much electron volt of energy is there? Electron volt is a small unit of energy. Joules will be too large to be measured. Okay, like if you ask some roadside beggar, how many trillion dollars do you have? He will be like, yeah, I have 10 to the power minus 10 trillion dollars. Very small, 0.0. For a beggar, why will you ask how many trillion dollars will you have? You can ask some big businessman, oh, how many billions or trillions you have. Same way, quanta of energy for photons is so small, you do not talk in joules. Joules is very big unit. You use electron volt. So this is one way, or also using 12400 by lambda. But then the lambda value will be in Armstrong. And yes, of course, this will be in electron volt. Is this absolutely clear, my dear warriors? Yep. Okay. So this is the entire modern physics. Yep. Correct. Awesome. Awesome. Next important thing. This speed of light, frequency, and lambda are related to each other like this. The speed of light is related to the frequency and wavelength by this particular formula. This is another important thing. Next important thing that you should be knowing about is the momentum, the momentum, the momentum of the photon. The momentum of the photon is given by h divided by lambda. Never ever use mass into velocity, because the mass of a photon is not defined at all. In fact, the mass of a photon which is moving is irrelevant, okay, it is irrelevant. Rather, you define only something called as the rest mass, and the rest mass is always taken as 0. This is considering the relativity effects. This is considering the relativity effects. Keep this in mind. Okay, so P is h by lambda. Also, you can see, since I can multiply and divide by C, hc by lambda c. So hc by lambda is energy. So this is also the energy of that photon, divided by c. Energy of that photon divided by c. So this is the energy of that particular photon divided by c. Everybody clear till this point? This c is also the speed of those photons. The speed of those photons. Mass is never ever defined. Now, last important thing over here is something called as the intensity of those photons, which is defined as how much energy, comes per unit time, per unit area, So this comes out as total number of photons into energy of each photon per unit time per unit area. So sometimes this is also written down as n by t into energy of each photon, which is hc by lambda, and then per unit area. This n by t is also the number of photons, per unit time, the number of photons which are coming per unit time. Keep this in mind. Everybody till this point absolutely clear? Everybody till this point absolutely clear? Okay, very good. Now, since the photons have momentum, since the photons have intensity, since the photons hit a surface and they can impart an impulse, so there will be also some force which is exerted on a surface. So that is called as the radiation force or the radiation pressure. The radiation pressure, my dear students, is nothing but the radiation force per unit area. Now, what the hell is this radiation force? It is nothing but the force due to the in momentum, change in momentum of photons. Change in momentum of photons is called as the radiation force. So when light particles, photons, hit a surface, they exert a force. So let's see what that value of the force is. First of all, say for example, you have, you have a surface like this, and this is another example. Okay, like this. Now this particular surface is completely absorbing surface. That means it absorbs all the light falling on it like black surface. This is a reflecting surface like a mirror or a polished surface. This is a reflecting surface. So if by chance photons are falling onto it, that means light is falling onto it here. Here light is falling onto it, but also do not forget it is getting reflected back. It is getting reflected back. So in the first case, that particular force or which will create that pressure is given by the pressure. The pressure is given by I, intensity of light, divided by C, intensity of light divided by C. Okay. Now, if you want to find the force, you multiply it by area. Pressure into area will give you the force. So this is the force while it is absorbing. When it is reflecting, then that same pressure will be exactly double. 2 times intensity divided by speed of light. This I stands for the intensity of those photons. This I stands for those intensity of those photons which is falling onto it. How intense that beam is. If it is very bright light, that means many photons are there. It will cause huge force, radiation pressure. If the light is very weak, then it will not cause too much of force. So normally, if I'm walking under sunlight, will sunlight be hitting my face and causing some pressure? Yes. But is that pressure noticeable? No. Yeah, forget the heat part. I'm talking about force. Does it feel like when you walk in the sun, somebody slapped you? Does it feel like that? No, right? Nobody applied force on you. It doesn't feel like that because that intensity of light, even though the sun is very bright, is not so much to cause a force of 10 Newton, 20 Newton, 100 Newton. Okay, that force is there, but it is so small that maybe a very small, tiny virus or microorganism only can notice it. Is it okay? All right. Yes, Jojo, that's the plan. All right. Pavitra, the lecture will go until easily 9, 10 o'clock. All right. Great. Now, since you have understood what are the 3 different ways of producing electrons and what is a photon, which is a particle nature of light, and its energy, its momentum, its mass, its intensity, and the force. So now it is a good time to talk about this particular phenomena where light is falling on a metallic surface. Obviously, it will impart some force, or obviously, it will ask these electrons which are in those atoms, hey, come on, get out, get out, get out, get out, get out, get out, get out. And these electrons will get out of it. And that is why that photoelectric effect is happening in the first place. So let's imagine a metallic surface like this. Let's imagine a metallic surface like this. Why metallic? Because metals can easily, freely donate electrons with some little bit of effort only. You don't need too much of effort. All right. So we have light falling onto it. We have, let's say, light falling onto it. We have light falling onto it. This is light which is falling onto it. So then these electrons will start coming out of that particular surface, but all the electrons will not have the same energy. Can you guess why the electrons have different speeds, different directions, guys? Why the electrons have different speeds and different directions? Come on, quickly tell me. This is your metal surface. Can you guys quickly guess and tell me? The reason is simple. When that light falls, some of the light will be absorbed maybe somewhere on the surface. Some light will go little bit 2-3 layers inside. Some light will go 5-6 layers inside. So when that photon will strike that atom, that electron will be thrown out. But once that electron comes out, if it is inside those layers of that metal, by the time it comes out, it will hit 2-3 atoms. maybe it will hit some another electron on their way, maybe it will get applied some force and that's why it loses some energy. It might be accelerated, decelerated within those molecules. So by the time it comes out, it might have some less energy. Agree? Same thing, if that light which is falling is hitting the atom which is on the surface, then the electron which will come out will not interact much with any of the neighboring atoms. It was on the surface, it came out, and as soon as it comes out, it will have a good value of energy and it will not lose any energy to any other atoms or collisions. So that is the reason why it has a range of speeds. Hello Ashwika, good evening. Good evening. No issues, just join in. It's fine. Hi Parama, good evening. Welcome. So, can I say that the energy of those photons which is incident is going in two things. Number one, pluck it out from that metallic surface, I will need some minimum energy. Like um, when you go to your friend's place and you want to want to take permission from his parents because you want that friend to come with you, maybe to a restaurant, maybe to buy something, maybe just to chill out. So you seek some validation, permission from their parents. You need to do some convincing. Hey, don't worry, I will keep that person safe. No worries, we'll come back early. Same way, this light has to convince, has to overcome the power of the atom. The atom is holding that electron. The electron can't say, hey, Tata, bye bye, I will leave. No. Atom will say, why are you leaving? Stay here, come back. Where are you going? Come back to the house. The photon which is falling has to give enough energy to overcome that barrier, to overcome that, whatever energy is required. So there is some energy which is required, which is called as the work function of that particular metal. And then whatever is remaining, maybe the photon had 100 laddus of energy, 20 laddus went in convincing that electron, please come with me. So the remaining 80 laddus, what will it be? The remaining 80 laddus, what will it be for? Yes, it will be the kinetic energy. It will be the kinetic energy of that particular electron. But remember, one more thing will happen. One more thing will happen. That electron which will come out will collide with some neighboring atoms. Electrons will experience some forces. So it will lose some energy. So some of the energy will also be lost during the collisions. Lost during basically the collisions. Is this understood, my dear warriors? This is a simple energy equation. This is a simple energy equation. Yes, there will be questions also after this theory. Then concept theory. I can't just do questions. Okay, I can't just do theory also. Now, in the best possible scenario, the luckiest electron will be something like this. The energy of the photon will be, the work function has a symbol phi. Phi is the symbol for the work function. How much energy is required to pluck out that electron? So that is called as a work function. Plus, the luckiest electron will have maximum kinetic energy and it will have no loss. And it will have no loss because it did not collide with anything. That's why it will have maximum energy. Anywhere it is lost, this energy won't be maximum. Is that clear? This equation is also sometimes called as the Einstein's equation for photoelectric effect. Einstein's equation for photoelectric effect. Is that clear? Now, we all know the energy of the photon can be written down as hf, or it can be written down as hc by lambda, where f is that frequency of light and lambda is the wavelength of the light which is falling onto it. This maximum kinetic energy can be written down as half m v max square, where v is the maximum speed of the electrons, beyond which it can't come. So if somebody asks you what is the maximum speed or some question related to the speed, obviously kinetic energy will be half mv square. That formula you can use. But is there a way to measure that kinetic energy? The answer is yes. So say for example, Say for example, what happens is, imagine this is your metallic surface. Imagine this is your metallic surface and light was falling onto it like this. Light was falling onto it. Light was falling onto it like this. So there were some electrons with low speed, some electrons with very high speed, some electrons with medium speed, some electrons again with some decent speed, some electrons with low speed, again some electrons with very high speed. So these electrons, what you do is you collect it on the other side. You collect it on the other side. And what you do is you connect a battery to it and try to slow down the electrons. Try to slow down the electrons. How do you try to slow down those electrons? Obviously, apply a electric field. So electrons are going like this. The force will be in this way. That means electric field will be in this way. So that the force on the electrons will be in the exact opposite way, so that it becomes retarded motion. You are retarding it, so you're slowing it down. So if the electric field is like this, that means this should be the positive terminal, this should be the negative terminal. So the battery which is connected is somewhat like this, this voltage that you apply, so that even the most energetic electron falls short of reaching the other side on the other metal. So you have increased the voltage to such a deal that this electron also is unable to reach here. It is slowing down, stops, and it comes back. That voltage is then called as the stopping voltage. That is called as the stopping voltage or stopping potential. Stopping potential. So in such a scenario, what happens is that if you had a ammeter, if you had an ammeter, the current flowing in the circuit will be exactly zero. If you do not apply sufficiently high voltage, then the electrons will be able to reach on this side. Once they reach on this side, they will go through this battery and they will complete their journey. Again, they will be emitted, complete their journey. Then you will see the current will not be zero. Okay, so if at all, the voltage is not equal to Vs, then obviously the current will be present. The current will be present in that particular circuit. So how much is the stopping potential? How do we calculate it? It's very simple, guys. It's very simple. I'll tell you what you can do. There is a formula in electric charges, electrostatics, which says that the change in the potential energy is nothing but the charge multiplied by potential difference. Do you remember this formula? Do you remember this formula, my dear students? Yes, I'm pretty sure you remember this. Voltage difference into charge is the potential energy difference. So, if the kinetic energy is lost in this process, where will it go? In the potential energy. So potential energy gained is basically coming from the loss of kinetic energy. How much is the kinetic energy lost? So how much is the kinetic energy lost? Obviously, that is your K max. All that maximum kinetic energy was lost. So that will be equal to charge into voltage difference. Charge is E. Each electron has a charge of E. Voltage difference is Vs. Voltage difference is Vs. So that is why you get K max as E times of Vs. K max as E times of Vs. So that is also something which you can substitute over here. If you don't want to put half mv square, it is also E times of Vs. Is that absolutely clear, my dear students? Very good. Now, last thing over here is that work function. This particular work function is basically the minimum energy required to pluck out that electron from that surface. Imagine your light falling does not have enough energy to pluck out and give kinetic energy, and then the losses not so much. It barely has the energy to just pluck it out. When it just plucks out, what will happen? You have just asked it to come out, but there is no kinetic energy. All the energy of the photon goes in just taking it out. So that minimum frequency of light, which just emits the photoelectrons is then called the threshold frequency, is then called as the threshold frequency. So if the threshold frequency is F naught, if the threshold frequency is F naught, HF naught will be the energy of the photon which will just take it outside. The energy of the photon which will just take it outside. So that much energy is then called as the work function. So can I not say that the work function is nothing but the Planck's constant into threshold frequency, or you can also write Hc divided by threshold wavelength. So F naught or basically lambda naught are nothing but the threshold frequency or wavelength. So it's very important to know that if and only if and only if F is more than F naught, then you will see photoelectric effect occurring. But by chance it is less than F naught, then photoelectric effect will not occur. Again, a very, very important thing. Okay. So only when the light's frequency is more than F naught, photoelectric effect will occur. If it is less than F naught, it will not occur, no matter how intense the light is. No matter how intense that particular light is. How intense that particular light is. Is this absolutely clear, my dear students? Everybody with me? Pakka? All right. Okay. Yep. Now, moving on to the next important thing over here. If you rearrange this equation, something like this, observe now. Imagine I write HF is equal to, I'll put HF naught plus, I will put E times of Vs. Now let me just rearrange this particular equation, guys. So what I will do, I'll bring HF naught over here. So HF minus HF naught is equal to E times of Vs divided by E. So H by E into F minus H by E into F naught is equal to Vs. Therefore, Vs is equal to H by E into F minus H F naught by E. Now compare this equation with Y is equal to mx plus c. Immediately you will start noticing H by E is m. This entire thing is your constant. Obviously F is like x, Vs is like y. So if I draw a graph, where I have frequency on the horizontal line and stopping potential over here, this graph will be a straight line with a slope of h by e, which is positive, and an intercept on the y-axis, which is negative, which means the graph should look something like this. It should look something like this, but it will not be existent below it. So I'll show a dotted line. So this is that intercept which I was talking about, which is minus hf naught by e, which is the same as minus phi divided by e. The slope of this line, will be h by e. Very, very important graph. This is very, very important graph. Slope is positive, the intercept is negative. Now, if you draw the same graph for any other metal, you will see always that particular graph will have the same slope, but it will have different threshold frequencies, different intercepts, because makes sense. This particular value will be different for every metal. For every metal, the threshold frequency wavelength will be different. So where it will hit will be different. But the slope, H and E are constants. So it will never ever change. Is this absolutely clear, everyone? Okay. Now, last things over here regarding the intensity and the current. something very similar to this only, Imagine you have a metallic plate here and a metallic plate here, and what you do is you have a battery like this, and I can change the voltage of that particular battery as per my free will. Light is falling onto it. Light is falling onto it. Electrons are getting ejected out. Electrons are getting ejected out. And in this particular circuit, there is a ammeter to check how much current is there. And you see what is the value of current for different voltages. Now, here is what happens. Guys. Very, very important thing. I will, second, sorry. I will put voltage over here. This is 0 and the current on this axis. Now, if the voltage is positive, it means you are not opposing the current, you are helping the current. When you are helping the current, I will call it forward biasing. You are trying to help and boost the current. When you are trying to stop the current, it is then called as the reverse biasing. You are opposing the flow of the electrons. What happens when you apply zero voltage? That means it's just a wire. Light falls, electrons are emitted. Some electrons will be able to reach here. Those electrons which reach here will constitute some amount of current. So there will be definitely some amount of current over here when there is no voltage. But imagine you help the flow of the current by applying voltage. So even those electrons which were losing all their energies and getting stuck in a loop, or they were getting stuck between the layers of metal, now because of that boost by that particular battery, you will see that they also will be able to reach here. So the current will naturally increase because more electrons will come out. So the current will increase. If you keep on increasing the voltage, don't expect the current to keep on increasing completely, because after a point, you will only be able to help as many electrons are coming out. When all the electrons which were getting stuck are helped and you are throwing them on the other side because of the battery's force, the electric force, then no more electrons are left to be helped. You cannot increase the current beyond a point. So you will see the current increases, but it becomes saturated after a limit. No matter how much you increase the voltage, nothing will happen. But on the reverse side, we have seen that what happens if you increase the reverse voltage, slowly the electrons get retarded and the current reduces eventually to zero. So this particular graph comes down over here. This will be the stopping voltage, Vs. Is this clear how this graph works? Now somebody will say, sir, what if I use high intensity light? Even if you use high intensity light, more photons will come, but still each photon has the same energy. So even then, even when the light is more intense, frequency of the photon has not changed. F naught is a constant. Vs will not change. It is not dependent on the intensity of the light. So that's the reason why even if you increase the intensity, the graph just goes like this. This is more intense light. More intense light. It just will have more current proportional to the intensity, but stopping voltage will not change. Saturation current will be more. That's all. In fact, there is a graph also for, how will the current react to intensity at any given voltage, and that graph comes out simply to be a straight line. It's as simple as that. Current is directly proportional to intensity. No intensity, no current. More intensity, more current. But stopping voltage has got nothing to do with intensity. Okay. So these are some of the important graphs and the theory points on photoelectric effect, the photoelectric equation, stopping voltage, stopping potential, threshold frequency, wavelength, and the properties of photons. I think now we are good to go and solve some questions. See, these graphs are already there. Okay. So let's solve some questions, guys. When there is a metal which is illuminated by a wavelength of lambda, the stopping voltage is V. If it is illuminated with wavelength 2 lambda, the stopping voltage is V by 4. The threshold wavelength is how much? Two scenarios, same metal, stopping voltage, threshold wavelength is asked. Let's think about the photoelectric equation first. The photoelectric equation being energy of the photon is work function plus your kinetic energy, which will come out of it maximum. Okay, let's take the two scenarios. Once when the wavelength is lambda, stopping voltage is V. So the light has a wavelength of lambda. So energy of photon will be hc by lambda, correct? Work function is phi only. Kinetic energy will be E times of V. Stopping voltage is V. Next time, when the wavelength is double, stopping voltage is V by 4. Stopping voltage is basically V by 4. So, when energy of the photon is hc by 2 lambda, because wavelength is double, work function still the same, stopping voltage V by 4. Great. I have got two equations now. Now look at the question what is asked. The question asked is, what is the threshold wavelength? To find the threshold wavelength, what do I need? Obviously the work function. We will need the work function, correct? So how do I find out the work function, guys? How do I find out the work function? If I subtract them, phi will get out. I don't want that. But can I get rid of V somehow, because answer has only lambda? So I have an idea. Why not multiply this entire equation with 4, with the number 4? So if I multiply this entire equation with the number 4, so 4 by 2 is 2. So 2 hc by lambda is equal to 4 phi plus E times of V. Now I have an idea over here. I will take this equation and this equation and I will subtract the two. I will subtract the two equations. This equation minus this equation. So it will be 2 hc by lambda minus hc by lambda is equal to 4 phi minus phi. 4 phi minus phi plus this and this. That's it. EV minus EV. Best part, they will get cancelled. So this will become just hc by lambda is equal to 3 times of phi. But wait a minute, work function is hc by lambda naught. So that is hc by lambda, of course. Hc cancels. So lambda naught will be 3 times of the wavelength. So 3 times of the wavelength, that means answer will be C for Captain Shreyas. Very good, Atluru. Is that clear? Is that absolutely clear how to solve this question? Does it look very difficult now after solving it step by step, understanding it properly? That is what you need to do. If you spend time analyzing how to do the questions properly, then as you proceed, speed will automatically build up. But build that confidence, my dear students. Next question. The threshold frequency is this much. Light's frequency is this much. Obviously, it is more than the threshold. So, the cutoff voltage is how much? Meaning, the stopping voltage is how much? That is what the question is. So, the question is, what is the stopping voltage going to be? So, here is what we can do. Let's use our equation. HF is equal to HF naught plus E times Vs. Planck's constant 6.6. Okay, we can put it later on also. First put H value into frequency. The question is only to find the stopping voltage, right? Yeah. Okay, so we'll do one thing. Before substituting, we'll just arrange it. So HF minus HF naught is equal to EVS. So Vs will be H common, F minus F naught, the whole thing divided by E. That's it. Now let's substitute the value of H, which is 6.6 10 to the power minus 34. The whole thing divided by 1.6 10 to the power negative 19, which is the value of E, multiplied by the difference of the frequencies, which means 8.2 minus 3.3, 3.3, the whole thing into 10 to the power 14, guys, into 10 to the power 14. You can see 14 and 34 will become minus 20. This minus 20 and minus 19 will become minus 1. So is that right, guys? So this will become 6.6 into, this will be 1.6 below. You can also write it as 66 if you want, divided by 16 into 8.2 minus 3.3, and 14 and minus 34 is minus 20. Minus 20 and minus 19 is minus 1. So 10 raised to minus 1, that's it. So that is what is going to be remaining. Now you can easily calculate it and see if you are getting the answer close enough to 2 volts. So you should get the answer close enough to 2 volts, guys. Is that okay? Everybody with me? Yeah. Yeah, logic gates will also be there in this particular session. Yes, logic gates will also be there in this particular session. All right. Let's go. Let's go to the next question coming up on your screen. Let's go to the next particular question coming up on your screen. Here we have a question which says, okay, I think this was again very similar, guys. This is similar model. If a wavelength is falling, the stopping voltage is 3V. If the wavelength is 2 lambda, then the stopping voltage is V. Then what is the threshold? I think we just did this kind of question. So I'm not going to repeat the same thing. I feel you should be easily be able to do this particular question as homework. Easily, you should be able to do this as homework. Same model, just I have done it. Same model, I have just done it. Is that right, everybody? You'll be able to do it? Paka? Very good. Awesomeness. So before going ahead, let me just give you one more question on my own. Observe this carefully. The stopping potential of stopping potential when light photon of 6 electron volt falls on a surface is 2 electron volt, sorry, is 2 volts, then the work function is how much? Then the work function is exactly how much? Come on, let's see if we can figure this out. The stopping voltage when light's photon of 6 electron volt falls on a metallic surface whose you know uh, whose stopping voltage is 2 volts, then what is that work function? That is the question. Let's go by energy equation. Energy of a photon is the work function plus E times of stopping voltage. The energy of the photon is 6 electron volt. Okay, this is 6 electron volt. Work function is asked. Stopping voltage is just 2. So what is phi going to be? It will be 6 electron volt minus 2. This is electron volt only. Yep. So energy of the photon is 6e, means you can think of it as if it is 6 electron volt. So when you subtract it, 6e minus 2e, this is just going to be 4e. So basically the energy of that work function will be 4 4eV. Yes, 4 electron volt is the answer. 4 electron volt is the answer. Very good. Excellent, guys. Awesomeness. Awesomeness. Let's go to the next question coming up on your screen. Here it is. The bulb is having 60 milliwatt power. Wavelength is given. The number of photons by the bulb per unit time. I feel that this question is related to the intensity related question which we just or intensity related formula which I just told you about. Sir, what can I refer to for model papers and PYQs plus last minute revision? Hence, model papers and PYQs. plus last minute revision hints means I didn't understand, Pratishtha. What are you exactly asking? I didn't get your question. Can you explain it a little bit better? The power of a bulb is 60 milliwatts. The wavelength of the light is 6000 Armstrong. What is the number of photons per unit time? I just know the formula for power. Power is how much energy is flowing per unit time. So it is the total energy per unit time. Perfect. What is the total energy? It is the number of photons into energy of each photon divided by time. So it will be n by t, and energy of each photon is hc by lambda. Oh, so I have to find what is n by t. So think about it, what n by t will be. Power will be there on the top. This hc will come below, and of course the lambda will go on the top. So this is exactly what we have to find, the number of photons per unit time. How much will that come out to be? What's the power? 60 milliwatts. So 60 into 10 to the power negative 3. Lambda, I think it's given 6000 Armstrong. So 600 into 10 to the power negative 10 to convert Armstrong into meters. Planck's constant just given as 6 into 10 to the power minus 34. And lastly, the speed of light 3 into 10 to the power 8, guys. I think this calculation is little bit simpler because 6 will cancel. 6 by 3 is nothing but 2. Then we have this 0 here, these 3 zeros here. So 10 to the power 4 and then 10 to the power minus 10 over here. This minus 34 and 8 will basically become 10 to the power minus 26. So check this out, 2 into 10 to the power something. There is only one answer like that. Come on, guys. So this will be minus 6. Just check it out, everyone. Yep, this is 6 into 10 to the power minus 34, 3 into 10 to the power 8. Yep, okay, this is also fine. Just check it out. Come on, guys. How much are you getting then? Option C, 2 into 10 to the power 10 to the power 17. Just check it out. 2 into 10 to the power 17 photons per second, which is option C. Just check it out, guys. Very good. Awesomeness. Happy evening, Krishna. Good evening. Nice to see you guys back. Very nice. Perfecto. Option C is the correct answer. A photon having certain momentum has energy E. If the momentum of the photon is made double, then the energy will become how many times? Energy will become how many times? I'm so glad, Prakrutik. Yeah, these videos will be definitely helpful for all the students for the last minute preparation. And Prakrutik, I am not remembering your name so clearly. Maybe has it been long time? Okay, come on, my dear students. How to solve this question? Is momentum related to energy? Yes, momentum is h by lambda, which you can also write as hc by lambda, again 1 by c. hc by lambda is nothing but energy, so it is energy by c. Clearly, momentum is directly proportional to energy. So if the momentum doubles, energy also doubles. There is a direct relationship. So that's it. It should be 2E, which is C option. Yep, directly. Directly. Very good. Awesome. Yeah, C for Captain Shreyas. Krishna, very good. Fantastic. Warrior Pandu, I hope you two are doing great. And welcome back to the Zero to Hero series. We had an amazing series, by the way, just last week, which was the 400 booster series with 100 questions, right? Those were really amazing. I hope you have seen that. If you have not yet seen it, please check it out. Okay, those were some amazing problems from the entire syllabus. Cool. All right. Let's move to the next question. The energy of a photon is 3 kilo electron volt, energy of the photon. What do you think is its momentum? We just saw that the momentum of that photon is energy divided by C. So this energy is 3 kilo. Kilo is 10 to the power 3. Electron volt means 1.6 into 10 to the power minus 19. This will be in joules. So from electron volt, if you want to convert, substitute the value of E over here, you will get it in joules. Speed of light is 3 into 10 to the power 8, guys. 3 into 10 to the power 8. So come on, What will it be, guys? Come on, think about it. 3 will cancel. So only 1.6 will remain into 10 to the power something. Now 1.6 is only there in option B. So I think it should be B option. Perfect. It is B option. But if you want, you can make out the powers. This 3 and 8 will cancel. This will become 10 to the power 5 will go on the top. So it will become 10 to the power minus 24. Units will be kg meter per second. Momentum, mass into velocity. Mass into velocity, kg meter per second. So which is B option. Perfecto. Very cool. Awesomeness. Let's go to the next question on your screen. There is a beam of light which falls on a perfectly absorbing sphere as shown. Then what is the force exerted on that sphere? It's a beautiful question, and trust me, lot of students will make some kind of silly mistake in this. What is the force acting on it? Let me tell you one thing. See, we know that the radiation pressure for absorbing surface is I by C. So the radiation force is nothing but the pressure multiplied by the area. Now the pressure is I by C, area is basically A. So whatever force I want to find, the radiation force which I want to find will be IA divided by C. Intensity is given, area we have to find, C is there. I can see I by C, I by C, I by C, I by C. So the challenge is not that formula, the challenge is what is that area. Now can you guys think and tell me what that area will be? Can you guys think and tell me what that area will be? Okay, think about it. Well, I'll tell you what. Just imagine that particular sphere. Just imagine that particular sphere, something like this. It's a three-dimensional sphere. Now just imagine those light particles coming through. Now just imagine those light particles coming through. Some will miss it. Some of them will obviously hit here. Some will hit here. Some will hit here. Some will hit here. Maybe some will hit here. So, lot of places, guys. Some will obviously miss it. Now, can you guys guess the area which will create that force? I know it is falling on that hemisphere. If you visualize it, only technically one side of that particular sphere is getting affected. The other side is completely dark because light is only coming from this side. But be careful, guys. What happens is, even though the light is falling on the curved surface, the effective area that you will be considering, the effective area that you should be actually considering is only going to be this much, which is the area of the circle, which is the area of the circle, because whatever photons pass through that circle will also hit that hemisphere. Now, whether it's a hemisphere or whether it's a quarter sphere, whether it's a square, whether it's some other weird shape, how does it matter? If 100 photons having certain momentum are stopped, they will exert some force. Now, when they are stopped, where they are stopped, it doesn't matter. On the hemisphere, they will be stopped at different places. On a circle, it will be stopped all at once. Fine, doesn't matter. They will have the same momentum. All that momentum is absorbed in that impulse. So the force will not change. So only consider that area of the circle, which is like the projected area for that hemisphere. It's like the shadow of the sphere will be a circle. So whatever photons pass through that circle will also end up meeting that sphere. So hence it will be nothing but pi r square. Yes, pi r square. So hence the answer is I pi r square by C. I by C, pi r square. Is that clear? I by C into pi r square. Absolutely clear? Okay, I meant some sort of reference containing PYQs and hints. Okay, so you want a question bank? Is that what you're asking? Which has some kind of PYQs and hints? Well, it is available in the pedagogy. If you have not yet seen that, it's right over here. So we have this called as, if you go to my classes in Vedantu only, okay, so see this, study from top books, just click on it. It will load up all that digital versions of all the books, MTG, Disha, so many publications are there, digital versions. You can choose what kind of question bank you want. Okay, so these are the smart books. You can, let's say practice, I want to practice, okay, or you want to create your own test. All right, let's say, I think, so these are the books. Let me just say create my own test, create your own test, and you say over here, create a custom test, you select which chapters you want. Okay, I want these chapters. Then say next. Say, should it be random? Should it be previously answered incorrectly, asked in previous exam, bookmarked, anything? PYQs you want, what time limit you want, how many questions you want, all these things you enter, and exactly those chapters, those kind of questions will be created. So use these question banks for practice. That's what I would say. These are the best things for practicing. All right. So this is done. All right. Let's go to the matter waves concept. All right. Now, see guys, light has dual behavior. Light has dual behavior, meaning light can behave like a particle, which we call as the photon. Sometimes it can behave like a wave, which is nothing but electromagnetic wave. There is a separate chapter only for it. Okay. Now observe this carefully. Just like light has dual behavior, de Broglie thought, can't matter, everything around us, atoms, molecules, protons, neutrons, electrons, they are matter. They also should exhibit dual behavior. So he said matter, he said matter also has dual nature. Matter also has dual nature. The particle nature, of it, right? It has that mass. Yeah, it has that mass. The wave nature of it, is called as matter wave. So a proton, electron, atom, we, the table, the fan, the building, the earth, everything is matter. So we know it has mass, it has velocity, it has kinetic energy. It also has another behavior, another side of its personality, which is called matter wave. Unfortunately, or fortunately, whatever, you cannot see this matter wave, but this light definitely I can see. So a lot of people think, and when they explain also, I've seen teachers saying this, if you have a cricket ball, then it has a matter wave associated with it. The matter wave's wavelength is very small. That's why you can't see it. Forget the wavelength is small. Even if it was big, you cannot see it, because it is not that when I say there is a matter wave, the matter particle is going like this, like a dancing duck, or I don't know what. It is not going like this, like a wavy ball or anything. No, no, no. That is not what it is. It is a different kind of wave which you cannot see it. Okay, so forget about that quantum part, but just imagine there is a matter wave which you cannot experience, feel, see, etc. Okay, just like Wi-Fi signal. Can you see a Wi-Fi signal, Bluetooth signal, X-ray? Can you see X-ray? No, right? You are not X-Men or somebody special, superpower. You cannot see it. Yeah, keep that in mind. All right. So, particle nature, let us see the characteristics. It has kinetic energy given by half mv square. The mass can be anything. The mass can be obviously anything. The momentum is mass into velocity. Then you can also say the velocity can be anything that you want. The particle can move with any velocity. But when you talk about light, the energy of that light is h into f. The mass, rest mass, is 0. Otherwise, it is not defined. momentum is never written down as mass into velocity, and the velocity has to be the speed of light. It cannot be anything. That is the basic difference between light's particles and matter's particles. Similarly, if you talk about the wave nature, the wave nature of this matter wave has a wavelength called as lambda, which is also called as de Broglie wavelength. De Broglie wavelength that is given by h by p. That is given by h by p. Here, that particular lambda is also h by p only, but this p is the momentum of that light particle. Sometimes you can also write it as energy by C. Lambda is, sorry, you cannot write energy by C, my bad. That was momentum. So this is h by p, which is also related to the speed of light as f into lambda. So this is for light. For matter, that momentum is calculated as mv. That momentum, if you divide, you will get the wavelength of that particular matter wave. This is the wavelength of that particular matter wave. This is your matter wave. Matter wave. So, if I have a mass having certain momentum, the matter wave associated with it is given by h by p. That is all that is there. Now, keep in mind that you can find the momentum either by mass into velocity. You can also use another formula, which is root of 2mk, because kinetic energy is also momentum square by 2m, which you have learnt in 11th standard. All these formulas are only valid for matters, but for light, it is completely different. Please understand that. Is that absolutely clear? Can we solve some questions on it? Can we solve some questions on it, my dear students? Shall we start with some questions? Okay, so let's gear up for some questions. Let's see whether you can solve one of the most fundamental questions. Can you guess the momentum of a photon whose wavelength is 0.5 Armstrong? Wavelength of a photon whose wavelength is 0.5 Armstrong, guys. Come on, think and tell. Think and tell. What's the wavelength of a photon whose wavelength, sorry, momentum of a photon whose de Broglie wavelength is 0.5 Armstrong? Simple. We know lambda is h by p. So if I substitute 6.6 into 10 to the power minus 34, okay, that is momentum, and the wavelength is nothing but 0.5 Armstrong. So into 10 to the power minus 10. So therefore, the momentum will be 6.6 10 to the power minus 34 divided by 0.5 into 10 to the power minus 34. 0.5 is half. So 2 into 6.6, guys. Yep. Come on. 2 into 6.6, 26 and all is there. So it will obviously become 13.26 approximately. And this will become, oh, sorry, this was Armstrong, my bad. This was minus 10. So this will go on the top. This will go on the top. What will it become? Yep. This will become minus 24. Plus 10 minus 34 is minus 24. So 13.26, 10 to the power minus 24 kg meter per second, which is there as option C, I think. Yes, C answer is correct. Perfect. Very good, Dream. Srinivas, crystal clear. Very good. Awesome. Awesome, guys. Awesome. Awesome. Let's move to the next question. The graph between the energy logarithm and its de Broglie wavelengths logarithm is what? Energy and lambdas logarithm versus logarithm graph. Log graph, guys. How to do this? Let's think. The de Broglie wavelength is h by p, which is also h by root of 2 times mass times kinetic energy. Okay, great. So lambda will be equal to, let's see, h by 2m is a constant. So let me just put it as a constant. And I have 1 by root k, which is root of energy. Basically, that constant over here is nothing but h by root 2m. Mass 2h, all are constants. Now, there is a reason why I'm doing it. You will see why. So lambda will be constant multiplied by e raised to minus half. Now take logarithms on both sides. So log of lambda will be log of constant plus log of e raised to minus half, which is log of a constant, which is nothing but another constant, I can say, a new constant. Power will always come outside, so minus half log e. So that is your log lambda. The question is log lambda versus log e graph. So obviously you can see this is like your y-axis. This log of e is like your x-axis. So what multiplies with x is mass, slope, and this is your constant. Y is mx plus c. So constant is positive, slope is negative. Negative slope only there here, C option. Can you see there is negative slope over here, and this is a positive y intercept. Positive y intercept right over here. C is positive, slope is negative half. So it has to come down. Yep, option C. Amazing question, right? Where you have to take the logarithm on both sides. It's a beautiful, beautiful thing. Okay. Now let's go to the next question. NEET 2020, an electron is accelerated by V volts. The de Broglie wavelength is this much. The potential difference is how much? Now let me tell you guys. See, when you have this formula to find de Broglie wavelength of matter waves, there is a special formula for electron only. Lambda is h by p, and this p is nothing but root of 2m into kinetic energy. Now, if I go further and say, where will this kinetic energy come from? Where will this kinetic energy come from? It will come because you have accelerated the charge through a voltage. So, that kinetic energy will be the charge that you accelerate into the voltage difference by which you accelerate it. So this is the formula which you will use in general whenever you have a charged particle accelerated. So this is a general formula. But if you make it more specific for only an electron, where this lambda will be 6.6 10 to the power minus 34, which is common value, root of 2 times mass of an electron, which is 9.1 10 to the power minus 31, charge is 1.6 10 to the power minus 19, voltage difference is delta V, and then okay, this lambda you try to convert it into nanometers or whatever. That lambda in general, very important guys, comes out as 1.227, whole thing divided by root of the voltage difference, but the answer will be always in nanometers. This is only and only valid for whom? Only for electrons. Only for electrons, nobody else. This formula you can use it for alpha particles, protons, electrons, anything, any charged particles you can use it. This is the only difference. So now it's very easy to find it out. So guys, the value of lambda is given to us. It is 1.227 into 10 to the power minus 2. This is 1.227 on the top divided by root delta V. This and this cancels. So this will become 1 by 10 square is 1 by root delta V. So therefore 1 by 10 raised to 4 is 1 by delta V. So delta V is 10 to the power 4 volts. So 10 to the power 4 volts is B option. B option. So you should know this general formula. You should also know that specific formula which comes always in nanometers. Nanometers, and there is a root of delta V. Root of delta V. Great. Let's go to the next question. The de Broglie wavelength of a neutron in thermal equilibrium with heavy water at temperature T and mass m is, come on, very interesting question guys. The de Broglie wavelength of a neutron in thermal equilibrium with heavy water at temperature T and mass m is, guys, if it is in thermal equilibrium, that means the kinetic energy of the kinetic energy is the same. The kinetic energy of that neutron on an average is the same as the kinetic energy of that heavy water, kinetic energy of that water. So if the temperature of this guy is T, so this guy is also T. So this is all average values of the kinetic energy. So how is kinetic energy related in general? How is kinetic energy related in general to the temperature? I think you remember this. Yep. What is it? Kinetic energy is 3 by 2 kT. 3 by 2 kT, that is your kinetic energy. Kinetic energy, let's say I call that symbol as E. This is from kinetic theory of gases. 3 by 2 kT. This K is your Boltzmann constant. Boltzmann constant, if you remember correctly. Oh, got it now, sir. So what next? What next? De Broglie wavelength is h by p and momentum is root 2 m times energy. So it will be h by, you have 2 times m. Instead of energy, you will put 3 by 2 kT. So this will become h by 2 cancels root of 3m kT. So this is your de Broglie wavelength and its relation to the temperature. So when the molecules, the particles have some temperature, they will have some kinetic energy, they will be moving with some momentum. So they will have a wavelength because of that movement. And that movement is there because of the temperature. So the usage of kinetic theory of gases in this particular concept. So I think D option is the most appropriate option. Yeah, D for doctor, D for Diksha ma'am, perfect. D for Delhi, Ames, perfect guys, perfect, perfect. Great. All right. Let's go to atoms and nuclei. Ready for it? Some basic theory regarding atoms and nuclei. Some experiments which you should be aware of. Before this, you should know the Thomson's model of atom. So, Thomson's model of atom. What was that Thomson's model of atom? What was Thomson's model of atom? He said that the atom is like a sphere, like a cake pudding, where the positive charge is distributed evenly. Positive charge is distributed throughout the atom. Distributed on that atom, and the negatively charged electrons are spread evenly across, and these negative charges are being pulled from all the sides by those positive charges. The negative charge holds the positive charges, and that's how the atom stays intact. So there are these electrons which are concentrated and holding the opposite charge This is exactly what Thomson's model did, and it was able to talk about the neutrality of atom. Atom is electrically neutral. Neutrality of the atom. It also predicted about electrons and protons. Electrons and protons. It was able to explain the conduction of electricity. It was able to explain the conduction of electricity, but it was not able to explain many other things, like how how are you getting atomic spectra, or there was an experiment conducted by Rutherford, how that gold foil experiment is yielding those results. All these things it was not able to explain, and quantum phenomena, so many other things. So then comes the next model, which is the Rutherford's model of atom. So as per the Rutherford's model of atom, the positive charge is not distributed throughout, rather it is concentrated in a very small region, and the electrons then the electrons are going around that small concentrated positive charge, which is called as the nucleus. Most of the atom is obviously empty. most of the atom is mostly empty. The nucleus has that concentrated charge. The nucleus has that concentrated charge. The electrons now are going in orbits. The electrons now are going in orbits around that particular nucleus. That is what Rutherford was able to tell. But although he explained neutrality, although he explained how the atom is relatively empty, positive charge is concentrated at the center, electrons are going round and round, and there is electric force of attraction. This electric force of attraction is the reason for the centripetal acceleration, and that is how it is able to perform circular motion. It was not able to tell many things like why atomic spectra is there, how come an accelerated charge is not able to emit any radiation and collapse into the nucleus, because when these electrons move around, they are accelerated, because uniform circular motion is accelerated motion. So ideally, by Maxwell was another guy who said any charge, if you accelerate it, gone, it will start losing energy. So how come this electron is not losing energy? And if it lost energy, it should slowly lose energy and fall into the nucleus. That will lead to the destruction of that element or that atom, which is not observed. We know atoms are stable, and that's why the entire universe is working the way it is. Else everything would have collapsed within no time. So it was not able to explain why there is no radiation and all of that. So that was Rutherford's shortcomings, and he performed the gold foil experiment, which looks something like this, I believe. Where is it? I think I have it somewhere. Yeah, Rutherford scattering. Look at this. This is a very interesting simulation. Let's have a look, guys. Like a watermelon. Yes. Guys, do you know watermelon? Say watermelon. So let me eat watermelon. Yeah. Exactly like the seeds of a watermelon, guys. Yeah. So just like a watermelon has the seeds inside, the seeds were the electrons. The watermelon was the positive charge. That was Thomson's model, by the way. Okay. Just in time, watermelon saved me. Wow. So this is that watermelon model. See, this is that watermelon model. See, exactly like this. This red part is like that watermelon. The seeds are there over here. Yeah. So that was Thomson's model, by the way. All right. So if Thomson's model were true, then the atoms would be not relatively empty. It would be like crazy. The alpha scattering experiment will not work properly. But now see now what will happen if I use Rutherford's model. All right. Okay. Now observe this. All right. So let's leave some traces. Okay. And let's start. Yeah. Throwing these alpha particles. These purple things are alpha particles. See, most of the alpha particles are going normally because the atoms are empty. Some atoms will get deflected. Zoop, zoop. Can you see why? Because this is nucleus. Nucleus will repel that alpha. Alpha is positive. Very few very few alpha particles you will see get deflected by large angles. Getting 180-degree deflection is very, very rare. I'm waiting for that 180-degree deflection. See, almost like obtuse angle deflection happened here. Okay, deflecting here. So it will take some time, guys. I mean, to see 180 degrees deflection. Yeah, let me try to increase the number of protons and neutrons. Most of them are going straight. Very few of them deflected by very large angles. Some are deflected by some decent angles. Oh, good deflection, guys. Why? The moment it encounters that positive charge, doop. So that is what exactly happens. So these alpha particles are getting deflected because of this nucleus. Okay, otherwise they will go normally as it is. This was Rutherford's experiment. Isn't it fascinating, guys? Now this made me very hungry, guys. Sorry, I'm eating watermelons. Yeah, but that's the way it is. Shreyas Sir is feeling hungry now. Pratyukshit, yeah, definitely. Why not? It will be helpful. Okay. But yeah, this is that beautiful setup. So alpha rays are bombarded on a gold foil with a heavy nucleus, which has a very heavy nucleus. Alpha particles are positively charged. They will be scattered, and then you find out how much they are scattered, and then those results were concluded. Okay. Let's see whether you guys can figure this out over here. When an alpha particle is moving with some speed, is falling on a nucleus, its distance of closest approach depends on the mass as what proportionality? Beautiful, beautiful question, guys. Okay. We also want, Sukanya, don't worry. When we meet, no, I will bring one big watermelon for all of you and we'll all cut it and we'll all eat it when I come to wherever you guys are, Hyderabad, Chennai, Bangalore to my meeting. So we'll bring one watermelon, we'll all share and eat it. But it is mango season now. More than watermelons, we'll eat mangoes, guys. Okay. So what is it? Huh. Alpha particle is coming like this towards a nucleus. This is a nucleus. Let's say the charge on it is plus Ze. Z is the atomic number. So what will happen? Eventually, it will start losing energy and it will stop before it turns around. Before it turns around. So the distance of closest approach is exactly this. This is the distance of closest approach when it stops. Now, the alpha particle has some velocity v. When it is very, very far away, then when it is very, very far away, the potential energy is negligible. As it comes here, it gains potential, it loses. What does it gain? It gains potential energy, and because of that, it loses kinetic energy. So when it loses all the kinetic energy, it would have gained maximum potential energy. So the loss in the kinetic energy is the gain in the potential energy. Kinetic energy lost is half mv square. Potential energy gained, it was 0. By the time it comes here, it will be Coulomb's constant. Charge 1, charge 2 of alpha particle is 2e divided by d square, divided by d. Do you understand this particular equation? These questions can come in the NEET examination. This equation is purely out of energy. Kinetic energy which it lost is the potential energy which it gained. Formula of energy is k q1 q2 by r. 1 by 4 pi epsilon naught is the value of Coulomb's constant. Can you see now? This mass is inversely proportional to d, or rather d is inversely proportional to the mass. So option D for doctor or Diksha ma'am is the correct answer. Is that right, everybody? Very good. No problem, Suganya. I'm so glad you guys enjoy the smallest of the smallest moments, the smallest of the smallest gestures. It really touches me when you guys say this, that you are happy uh, with the smallest of the smallest gestures. You guys will definitely do very well, very big in life. Okay, now let's come to Bohr's model. Okay. Now Bohr said that there are three postulates, and based on those three postulates, he gets everything. He said that, you know what, even though an electron is a charged particle which is accelerated, if it moves in a specific orbit, then the matter wave of the electrons undergo a standing wave interference, because of which it does not exhibit Maxwell radiation, and this is valid only in this specific state. Some crazy theories he came up with, but the way it is presented in your NCERT is very confusing and unnecessary, and I don't know, I don't like it. Anyways, coming to the point, he says that, let's say, for example, this is your nucleus which has Z number of protons. So Ze will be the positive charge. So this is your nucleus. This model or this theory is only valid only when there is a single electron. There could be multiple orbits, that's okay. That's fine, guys. There can be multiple orbits, etc. That's okay. But it should have only one electron in it. Why only one electron, guys? Why only one electron? Because if there are other electrons, there will be repulsive forces. There will be repulsive forces because of the other electrons. So it is only valid for single electron models of atom. So for helium, will it be valid? Yes or no? For helium, will it be valid? Yes or no? Come on. No, because there are two electrons. But for helium plus, yes, because one electron is gone, one electron is left. For lithium, no, because there will be three electrons. Lithium plus, no, one electron is out, two electrons are there. Lithium double plus, yes. Why? Only one electron will be left. Lithium double plus means two electrons left out of those three electrons. Yeah. We'll be doing a break, having a break after this atoms part. Okay. Don't worry. Now observe this carefully. Observe this carefully, guys. So there is a electric force of attraction. So there is a electric force of attraction, and that causes the centripetal acceleration, and these perform uniform circular motion, and these orbits are called as stationary orbits. They are called as stationary orbits. Why stationary, guys? Why stationary? Because not because the electron is stationary, but because the energy is fixed. The energy is stationary. It is not vibrating. It is not shaking. It is not changing its values of energy, radius, speed, etc. These are fixed, stationary. You cannot change any value on this. That is how it is. Okay. All right. So this particular force that is there, this particular electric force that is there, is given by m times centripetal acceleration. M times centripetal acceleration. This was one of the first things that he said. And this is nothing but v square divided by radius. This electric force is obviously Coulomb constant, into charge 1, charge 2 divided by distance square. This was the first important thing. The second important thing which he said was that the angular momentum is always n times h by 2 pi, which is quantized, basically quantized. So the electrons can only go in those orbits whose angular momentum is a multiple of h by 2 pi. This angular momentum is mass into velocity into radius. Mass into velocity into radius. Is this absolutely clear? Everybody till this point? Clear? Yes, no. Using these things, using these formulas, you can get everything. You can get everything. And the everything is as follows. Starting off with radius. The radius is basically 0.529 Armstrongs multiplied by n square by z. Basically, the radius is proportional to n square by z. More the value of n, more is the radius, more the size of the nucleus, as in the protons, that is more protons, the radius will start shrinking because it will pull those electrons towards the nucleus. So it is inversely proportional to z. So this is obviously a thing which you should remember. Same thing you will also get for velocity. You will see velocity is proportional to z and inversely proportional to n. Next important thing is the kinetic energy, which is half mv square, and potential energy, which is 1 by 4 pi epsilon naught ze into minus e divided by r. When you add both of them, you essentially get the total energy in any orbit of the electron, which comes out substitute the value of speed, substitute the value of radius, everything, the value of energy that you get is negative 13.6. Negative 13.6. Here you have n square, sorry, z square divided by n square, but this is again in electron volt only. Okay, so this has to be always in electron volt. Again, a very important relationship. Minus 13.6 z square by n square electron volt. If you see the value of kinetic energy, guess what? The value of kinetic energy always comes out equal to the negative of the total energy in that orbit, and the potential energy comes out, whatever this is, the double of it. So 2 times the energy in that particular orbit. Sometimes there could be some questions based on this as well. There could be some questions also based on what is the kinetic energy, potential energy, etc. on that as well. Is this clear? Okay. Next important thing, if you see any orbit, that particular electron will have its oops, that particular electron will have its de Broglie wavelength, So this will be lambda, which is your de Broglie wavelength. If the principal quantum number is n times lambda is always going to be the circumference of that orbit. Circumference of that orbit with the principal quantum number n. If the first shell is there, n will be 1, second shell n will be 2, third shell n will be 3, like that. So this is also very, very important, guys. Okay, the principal quantum number into the de Broglie wavelength is the circumference of that particular orbit. Keep all these things in mind. Cool. Very good. These were the first two postulates. Let's go to the last postulate over here, which gives us the atomic spectra and all of that. Okay. Now, imagine that particular electron jumps to another orbit. This particular process is then called excitation. Maybe it can also jump back to the original state or maybe some intermediate state. This is called de-excitation process. In each of this process, there is a photon which is involved. Very important. So if a photon is absorbed, such that the energy of the photon is the energy difference, then the electron will jump. And if the electron de-excites, then you will see photon will be emitted of exactly that much energy of whatever is the energy difference. So this is the third important thing, which is the energy difference between the orbits. When I say energy difference between the orbits, it is exactly this energy that I'm talking about, is nothing but h into f, or I can just say it is the energy of the photon which is emitted or absorbed. So if it is emitted, it is then the emission spectrum. It is absorbed, then it is the absorption spectrum wavelength. So depending on whatever is happening. Now, this particular energy difference, we can write it in electron volt, minus 13.6 by n1 square z square. Let's say minus 13.6 z square by n square. This is some another orbit. Energy of the photon hc by lambda. This is in electron volt. So I'll put E here also, redoing all the calculations and finding 1 by lambda. Redoing all the calculations and then finding the value of 1 by lambda. What is it that you are going to get? Come on, my dear students. Yep. What is it that we are going to get? What am I taking you to? What am I leading you through? Yes. What is it, guys, that I'm taking you to? Some hint. Come on. Rydberg. Remember? Rydberg. Do you remember? Very good. Very good. If you remember, 1 by lambda. After redoing the calculations will be Rydberg constant z square 1 by n1 square minus 1 by n2 square. Perfect. This is called Rydberg constant. Rydberg's constant, whose value is 1.1 10 to the power you have 7. Yes, 10 to the power 7. Is that right, everybody? 1.1 10 to the power 7. This is the Rydberg's formula. Very good. What is N1 and N2? N1 and N2 are the orbits between which the electron is transiting, where it is jumping, wherever it is jumping or it is transiting. Yeah. So this formula also plays a very crucial role in finding what is the wavelength which is emitted or absorbed in that transition. Now, you should know that if I plot the energy levels of these orbits, it will look something like this. The first gap will be very huge. The next gap will not be that huge. The next gap will be even smaller. The next gap will be even smaller than that. Next gap will be so close, virtually indistinguishable. And then they will come so close, you hardly can make out anything. So there will be many lines after this. And I will just show it like that. Here, okay. Some lines like this. So what are these? This is the first orbit. This is the second orbit, second principal quantum number, third principal quantum number, fourth, like that it will continue till you reach completely outside the atom. That means n is infinity. So this is free electron. This is outside the atom. This is basically outside the atom. Okay. Now, observe this carefully, guys. Observe this carefully. Imagine imagine there is an electron which is there in the ground state and you take it over here. This process is of excitation. This is its first excited state. First excited state. If I take that same electron to here, this will be the second excited state. This particular level was its ground state, meaning when it was grounded, when it was completely stable, it was not at all excited. That time, this was the ground state energy. First excited means the next orbit available to it. Second means the next orbit after the first excited state available to it. But if I give it so much energy that I take out this electron completely to infinity, then that is called I am ionizing it. So I am ionizing that particular element. It is becoming completely free electron. So I'm completely removing it from that ground state. That is basically then the ionization process. Is this absolutely clear? Everybody with me? Very good. Very good. Now, now, do you have to remember these values? Somebody has already pasted the values. Very good. Who is that? Dreams Unlimited. Very nice. So it's better if you remember these values for hydrogen atom. Things like for the ground state, it is minus 13.6 electron volt. Yeah. This is obviously 0 electron volt when it is completely free. Then for the second orbit, it is basically minus 3.4 electron volt. Then it is minus 1.51 electron volt. So this is how it goes. Okay. Then it goes to 0.52 and all of that. 0.8, all that. Okay. Everybody. So these are the energy levels, minus 13.6, minus 3.4, minus 1.51. So this is how it will slowly keep on increasing, and the gaps are not the same. sometimes they can ask you how much is this energy, how much is this energy, how much is this energy. If you take the difference of these two or this, you can easily get that energy. But please remember, these are for hydrogen only. If it was helium, then you have to multiply it by Z square. Z is 2 for helium. For lithium, it is 3. So this is only when the value of Z is 1 for hydrogen. Okay, coming back, that was excitation. What about de-excitation process? Very, very important, guys. So if at all the electrons in the higher excited states get de-excited and come down over here, they come down over here, let's say like this particular wavelengths which are then emitted, these wavelengths lie in the ultraviolet region. They lie in the which region, guys? Ultraviolet region. These wavelengths together are clubbed as Lyman series. What are they called? Lyman series. Very, very important. They are called as Lyman series. But if the electrons in the higher states come down to the second energy level, then those wavelengths emitted are in the visible spectrum: violet, indigo, blue, green, yellow, orange, red. Yellow being the average color, so that's why I use yellow color. So it's visible spectrum. That series is called as Balmer series. All these wavelengths together are called as Balmer series. But if you go slightly higher and the transitions are happening over here, transitions are happening to the third orbit, then, my dear students, they are in the infrared region, IR. They are called Lyman, Balmer, Paschen series. If it happens even higher, maybe to the fourth orbit or so and so, to n is equal to 4, like this, then it is infrared again, but it is then far infrared, very, very deep color of the infrared. This is sometimes called as the near infrared region, that is the far infrared region. So you get bracket, P fund and all of that. Is this absolutely clear, my dear students? Very, very important again. Now also keep in mind that since the difference of the energies is energy of the photon, which is hc by lambda. So if you want a large wavelength, the energy difference should be very small. They are inversely related. So say for example, Lyman series, you want the smallest wavelength in the Lyman series. Lambda should be small. That means the energy difference should be large. So if the electron transits from infinity to the first orbit, the wavelength emitted will be the smallest. The wavelength emitted will be the smallest. Very, very important. This transition will have the smallest wavelength in the Lyman series. Here the gap is small. So if the gap is small, lambda will be large. So from here to here, that wavelength will be the largest. Same thing even for Balmer series. From here to here, the gap is small. So the gap is small. So lambda will be large. Here, the gap of the energies is much wider. So lambda will be very, very small over here. So that's how it works. If you are asked what is the first line, what is the last line, what is the maximum wavelength, what is the minimum wavelength in any of these series, Okay, clear till this point? Yep. After this, yes, everything is in the infrared region only. So violet, ultraviolet basically, then it becomes visible and then it becomes red. Okay, that's how you should remember. Violet has L, no? Violet, ultraviolet, L for Lyman. That's how you can remember it. Yeah, now you will say, sir, Balmer also has L. Sir, how to remember that? Okay, now you have to make some other way then. Okay, or you can think of lilac. Lilac is purple, violetish color. Lilac is a color. So Lyman, lilac, violet, ultraviolet. That's also another way of remembering. Okay. So let's do some questions and then quickly have a break, guys. Ready for the questions? Quickly after this, we are going to have a break immediately. As per Bohr model, energy required to remove the electron from the ground state of a doubly ionized lithium ion. Come on, guys. Lithium ion. Yes, dinner break is coming after this. Lithium. Oh, to remove the electron from the ground state means completely you are taking it out. So basically you are finding the ionization energy will be 0 minus the ground state energy, the energy in the ground state. What is the energy in the ground state? It is minus 13.6 Z square, Z is 3, N is 1 electron volt. So minus minus becomes positive. So 13.6 into 9, guys. It's going to be a huge number. Yep. Come on, guys. 13 nines are 117. So it should be more than 117. There is only one number like that. 122.4 electron volt. No other number will come close to it. It is a D option. You don't have to sit and calculate it. Yeah. Very straightforward. Okay, very good. Let's do the next question. If the total energy of an electron in the orbit is negative 3.4, the kinetic and the potential energies are, the kinetic and the potential energies are, come on guys, what do you think it is? Yep. Total energy is this much. I just told you, kinetic energy is negative of the total energy. So negative of 3.4 is basically negative 3.4 is basically plus 3.4. So kinetic energy is positive 3.4. Potential energy, I told you, it is a double of the total energy. So 2 times of minus 3.4, which is nothing but minus 6.8 electron volt. That is the potential energy. Guys, that is directly there over here only. Option D again. Yep, very nice. Very good. D option. Perfectly. Awesome. Awesome. Let's go to the hydrogen spectrum related questions. Lyman, Balmer, Paschen, bracket, Pfund, Humphrey. So this is something which I had told you before also. Okay, let's see the questions on that. Ratio of the wavelengths of the last line of Balmer and the last line of Lyman. Lyman, last line. Last means always infinity. Lyman means number 1. Balmer, last line means infinity. Balmer means the number 2. So lambda b 1 by will be Rydberg's constant 1 by 2 square by 1 by infinity square, 1 by lambda of Lyman, Rydberg constant 1 by 1 square minus 1 by infinity square. So obviously take the ratio of them, meaning divide it. So 1 by lambda of Balmer by 1 by lambda of Lyman, RR will cancel. So 1 by 4 minus, what is 1 by infinity? 0. 1 by 1, what is 1 by infinity? It is again 0. So lambda of Lyman, lambda of Balmer comes like this. This will go top, this will come below. So this will be just 1 by 4. So the question is the last line of Balmer series and the last line of Lyman series. So if it is lambda b by lambda L, then it should be 4 by 1. It will be inverse. So 4 by 1 means C option. Yes, C is the correct answer. B by L is asked. Yeah, C option. Perfect, perfect, perfect. Great, great. Awesome, guys. Awesome. Let's go to the next question coming up on your screen. There is a light of 975 angstrom which is exciting the hydrogen atom. So imagine this is a ground state atom. It is going to an excited state. This was the ground state. So if it is reaching here and it is absorbing a wavelength of 975 angstrom, okay. So what is that excited state we'll have to find, because the question is what is the number of spectral lines coming out of it. Now, first of all, let's use our Rydberg's formula to solve this particular part. So 1 by lambda. Lambda is 975. So 975 into 10 to the power minus 10. Rydberg constant 1.110 to the power 7. 1 by 1 square minus 1 by n square. Okay. So this is just going to come down over here. So 1 by 975 into 1.1 into 10 to the power minus 10 into 10 to the power 7 is equal to 1 minus 1 by n square. So if I ask you what is 1 by n square, it will be 1 minus this whole number, 1 minus this particular number which is there, which is nothing but 975 into 1.1 into 10 to the power minus 3. So come on guys, that will be 1 by n square. Solve this, find the value of n that you get approximately from this. Solve and tell me approximately what is the value of n that you get from this. Approximately. Yeah. What is it coming out to be, guys? Check first what is n square and see what n is coming out to be. I have a feeling this should come out as 9 and maybe this comes out as 3. Just check out if it is coming out as 3 by any chance. If that is coming out as 3, means what? These are the energy levels. This is 1, this is 2, this is 3. Just see if it is 3 and 9 or is it something else. Don't find 1 by n square. Find n square. Yeah. See, number of spectral lines. If it was in the third state, then this one wavelength can come, this one wavelength can come, and after jumping here, then it can jump here. Then 3 wavelengths can come if it was in the third state. I think then maybe this is 4 and this is maybe 16. So if it was in the energy level 4, n is equal to 4, then this wavelength can also come. Maybe even this can also come. Even this can also come. Yep, these are the all possibilities that you get. Like this, like this, like this, like this, like this. All possibilities. I think 6 wavelengths are there. Maybe the answer is 6. Check it out. Yes, 6 lines are there. 6 lines are there. Whenever you have to count the number of lines, then use this formula. Use this formula always. N into n minus 1 by 2, where n is the excited state principal quantum number. The principal quantum number of that excited state. So if the excited state has a principal quantum number 4, so 4 into 4 minus 1 is 3, 4 3s are 12, 12 by 2 is 6. That's how you get it. So this is an easy way out. This is an easy way out for solving these questions. Cool? Understood, everyone? Awesomeness. Great. So that was answer 6, guys. Now, yeah, we'll come to nucleus, but obviously after a break. So, time for break, time for a break, and then we will continue. Time for a break, and then we will continue. We'll take a 20-30 minutes break, and then we'll return. All right, so we are back. Welcome, welcome, welcome aboard, guys. Yes, your captain Shreyas is back. Okay, so let's begin. Let's begin. Welcome back, Dreams Emperor, Jain, Atluru Krishna. Welcome, and let everybody know also that Shreyas Sir is back. Okay, great, great, great. Welcome aboard, everyone. All right. Okay. Okay. Hmm. So we get everything sorted. Okay. Yes. So let's begin with the nucleus chapter and then the semiconductors. Okay. So first of all, in this particular initial part, we understand the structure and the composition of the nucleus, where nucleus is made up of protons and neutrons. So let's say, for example, this is our nucleus. This is our nucleus. Inside the nucleus, you have protons. You have protons. And you also have neutral particles called as neutrons. So the blue ones are, let's say, neutrons. And the green ones are, let's say, protons. So this is neutron. The green one is a proton. Neutrons was discovered by scientist named Chadwick. Okay. Sir Chadwick has discovered the neutron. Thomson discovered the electron. Okay. And the concept of nucleus came from Rutherford, from that gold foil experiment. Okay. Now, by the way, outside of this, you will have your regular electrons and all that in different orbits. That is secondary. Now, any nucleus has a mass number. This is your atomic mass number, atomic mass number A, and that is a composition of number of protons. This is number of protons, number of protons, which is also called as also called as atomic number, not mass number, atomic number. And to that you add how many neutrons are there. So this is number of neutrons which are going to be present in it, number of neutrons which are going to be present in it. Any element, if this is the element, this is the nucleus of some element, let's say X, that particular element X will always have the atomic mass number written on the top and the atomic number written below over here. Like for example, hydrogen, I can put 2 over here, 1 over here if it is isotope, or say helium, 4 over here, 2 here, 2 protons, 4 protons and neutrons together. So totally there will be 2 neutrons in this. So that is what is the representation of any element. Now, by chance, if there are elements with the same atomic number, if they have the same Z but different number of neutrons, then they are called as isotopes. Then they are called as isotopes. If by any chance they have the same number of neutrons but different protons, then they are called as N for isotones. They are called isotones. Isotones are those elements with same neutrons but different protons. But maybe there are some elements with more protons, less neutrons, more neutrons, less protons. Their sum is constant, which means the same atomic mass number. Then they are called as isobars. They are called as isobars. Keep this in mind. Okay, till this point, everybody clear? Great. Next important thing is the radius of this particular nucleus. This radius, the radius of that nucleus is a constant into atomic mass number raised to 1 by 3. This is very important, guys. Again, this formula, the radius of this particular nucleus is R naught A raised to 1 by 3. R naught is a constant. Usually it is around 1.1, usually around 1.1 into 10 to the power minus 15, which is in meters, which is 1.1 femtometers, which is 1.1 femto. Femto is 10 to the power minus 15, like you have micro minus 6, nano minus 9, pico 10 to the power minus 12. So 10 to the power minus 15, femto or Fermi, anything, femto or Fermi, both will be okay. Fair enough. If you measure the density by any chance, the density of the nucleus, which is the total mass of the nucleus upon 4 by 3 pi radius of the nucleus cube, that will always be a constant. This is very, very important. Approximately 10 to the power something really huge, 10 to the power 27, if I'm not wrong, 10 to the power 27 or something kg per meter cube. Very, very large value. Okay. So this density is constant, and most importantly, it is independent of atomic mass number. It is independent of the atomic mass number. Okay. Yeah. Atomic mass number. Perfect. Now, you might be also wondering at the same time, how come the protons and which are positively charged staying together? It's like there are two guys who hate each other, like two Pandus, imagine. Okay, so that comes to the next part. Imagine there are two Pandus. They are positively charged. Obviously, they don't love each other. So they will repel, and there is electric repulsion between them. There is electric repulsion between them. But let's say you want them to be together for some party, for some event. It's like one get together is there. You want these two Pandus together. So what happens? One beautiful Champa comes in between. Beautiful Champa. So this is the girlfriend of this Pandu. This is the girlfriend of this Pandu. These two girlfriends are also friends with each other. Who are these girlfriends? They are neutrons. Yeah. So this Pandu is in relation. Girlfriend is this. This Pandu's girlfriend is this. These two girlfriends are friends. But these two Pandus don't like each other. Just because their girlfriend told, I have to go together for some function, they are all going together. Understood? So neutrons make that happen. In spite of the repulsion, you will see there is a new force between them. There is a new force between them, neutron, neutron, proton, proton, neutron, proton, etc. like this. That is basically the nuclear force, and the nuclear forces are much, much larger than the electric force, and remember, electric force is much, much larger than the gravitational force, obviously. But there is one thing about nuclear force. Even though it is the strongest force between the nature, which can happen between neutron proton or proton proton, or let's say neutron neutron, between the nuclear particles, they are extremely short range. You cannot expect them to apply forces even in Armstrong distances. So they are only within the nucleus. So typically in Fermi meters or femtometers, which is 10 to the power negative 15. 10 to the power negative 15. Champa, Pandu, welcome back. Yeah. This series is for both. It is for concept clearing, zero to hero, and then applying those concepts in the problems, which many NEET aspirants face difficulty in. So if you are a NEET aspirant struggling with physics, you want to boost your score by a big margin with a clear-cut concept in detailed manner with the application, with question solving, this is the zero to hero series for you, I would say. Okay. Also, it is not dependent on the mass, not dependent, it is not dependent on the mass or even the charge, like you can say it can act between proton, neutron, anything, and it only depends on the spin. It only depends on the spin of those particles. So this is something which you should be aware of regarding nuclear forces, which are the strongest forces in nature. Is this all clear, my dear students? Perfectly. Very good. So I think we can start doing some questions based on that. The nuclei of which of the following are isotones? Which of the following are basically isotones? Come on, guys. Isotones. The nuclei of which of the following are isotones means same number of neutrons. Same number of neutrons. That means A minus Z, which will be N, is going to be the same. So subtract this with this, see what it is. This with this, see what it is. Obviously, 92 minus 42 and 92 minus 40 won't be the same. So this is out of question. 84, 38, 86, 38 out of question. 40, 20, 16, 32, 20. And this is no, this is also out of question. This I think will work. 74 minus 34, 71 minus 31, guys. Aren't they equal? Aren't they equal? Yes, the number of neutrons are 40. So I think it should be option A. Yes, it is option A. Very good. A for Atluru. Shaurya A. Yes, Krishna. A for Ames. Perfect, Karthi. Perfect. Guru Baswaraj. Great, 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 great. Very good, Dreams. Very good. RBS edits. Hello, sir. I'm first time attending your live. Please see my message, sir. I have one doubt. Yes, buddy. Whatever doubt you have relevant to the topic, please let me know. Okay. Moving on to the next question, guys. The mass number of helium is 4. Sulfur is 32. The radius of sulfur is larger than that of helium by what factor? Mass number. That means we are talking about A. So they are asking the question on radius. I think there is a relationship which I just told. R is proportional to A raised to 1 by 3. Oh, so the radius of sulfur upon the radius of helium is atomic mass number of sulfur, atomic mass number of helium, the whole raised to 1 by 3. So atomic mass number of sulfur is 32. Atomic mass number of helium obviously is 4. The whole thing raised to 1 by 3. 32 by 4 is 8. So 8 raised to 1 by 3. So this will be 2 by 1. So that is Rs by R helium. This means radius of sulfur is 2 times radius of helium. That's it. So 2 times is the answer, which is C for Captain Shreyas. No, it's not 8 times. If you forgot 1 by 3, you will get some wrong answer. Yeah, it is C for your Captain Shreyas. Very good, Siva. C, very good. Guru Baswaraj, Krishna, awesome. Karthi, very good, Devil. Excellente, excellente, excellente. Very nice. Yes, Atluru. Very good, Narne. Very good, Dreams. Perfect. Perfect, my dear students. Okay. So let's have a look at the next question. The radius of some element 2713 is taken to be RAL. Then the radius of this element is approximately how many times the radius? Again, the same concept, guys. The radius is directly proportional to atomic mass number raised to 1 by 3. So the radius of that element, which is TE, upon the radius of this element, which is AL, will be atomic mass number of T upon atomic mass number of AL, and this whole thing raised to 1 by 3. Atomic mass number of TE is 125. Atomic mass number of AL is 27 raised to 1 by 3. Cube root of 125 is 5 because 5 square 25. 25 into 5 is 125. This is 3. 3 square 9. 9 3s are 27. So this is 5 by 3. So therefore, the radius of TE, radius of T, bring this on the top, will be 5 by 3 times radius of AL. 5 by 3, that is Baswa sir, Baswasaurus sir, biology. Yep, B for biology. Perfect. That is the correct answer. Very good, Atluru Krishna. Devil X Karthi, very nice. Some of you got the correct answer. Some of you gave the exact opposite answer, 3 by 5. So be careful what is asked in the examination. Great. Let's move to the next one. Okay, we're coming to mass defect, mass energy relationship and all. Now, Einstein Einstein, okay, so let's say this is Einstein. Einstein proposed a very interesting thing. He said that if you have some mass and you destroy it, then what you get in return is some energy. It is converted into energy. Energy is obtained. Similarly, he also said that let's say you destroy energy. You have energy. You have energy. And let's say you destroy that energy. So if energy is destroyed, then the exact reverse happens. You will see that mass will be created. Mass will be created. Just like your energy was liberated or basically created. This is the relation between mass and energy. And he said the relationship is as follows. Energy which is created or destroyed is the mass which is created or destroyed into c square. What is c? Obviously, we all know it is the speed of light. It is nothing but the speed of light, which is standard 3 into 10 to the power 8 meters per second. Is that right, everyone? Very good. Awesome. Okay. Sir, I'm weak in physics, sir. If I do high weighted chapters for physics and do PYQs and NCERT questions and mock test 10, if I do, can I get 115 physics? Please tell me, sir. Buddy, very, very good question. Let me tell you. So, this is only for NEET 2025. This would not be true for NEET 2024, 23, 22, 21, even 20. The last 4 or 5 years have been very predictable. This year, NTA has gone into the revenge mode. And we saw that it is not just with NDA, but even the CBSE board or even the state board examinations have been little bit more difficult when you consider the physics examination. So there is no guarantee, just like we saw in the JEE Mains January attempt, where the priority order changed when students studied high weightage. Completely unexpected questions came from the low weightage chapters, like say for example, fluids or solids. Lot of questions being asked. Reoptics, very high weightage, and then electromagnetic induction, hardly anything came. So the weightage rules never applied, and the same thing might be happening again for the NEET examination. So really speaking, we do not know what is high weightage now. If you go by the past trends and if you study those high weightage, what if the questions will come? It's not like it will not come, but it won't come as much as you're expecting it to come. That might not give you 150 score, that might give you 100 or maybe even 110 or even 90. So that is the reason why we should not play with fire. We should try to do as many things as possible. There is nothing like high or low weightage. Try to do high and medium weightage at least. Then 100% you can aim for 150 marks. Is that okay? All right. Cool. Yeah. Anyways, now if you write the mass in a new unit, there is a new unit of mass which you should know, which we atomic mass unit. So that is the reason why, guys, you can see that not just here, but even in our crash course, we are teaching all the chapters. We are not missing any chapters. Number one. Number two, we are teaching everything. We say that we do not know what might come, what might not come. We are preparing for the worst case scenario. And I feel it will benefit our students because when the exam happens, I am pretty sure our students will come and tell, at least my teacher had 100% taught me all the things. we have solved many questions. I was able to do, or I was not able to do for some or the other reasons, but at least I had seen all these things. But at least you will not come and tell me that, you know what, sir, I never studied only this subtopic, or I never did only these things. That you will never say in my guidance on this channel, in our crash courses, you will not say. That is why I'm going everything properly, slowly, steadily. Atomic mass unit, it is nothing but it is nothing but 1/12 the mass of C12 atom. It is approximately some 1.65 10 to the power minus 27 kg, which is a very small unit. So this is something which you should definitely know. Is that okay? All right. Now coming back to this, if this mass was in kg, it is okay. This particular mass right now was in kg, but let's say this mass was in atomic mass unit, and I do not want it in joules. This energy obviously was in joules, SI unit. This was the SI equation. What if I putting this mass in atomic mass unit, and I want this particular energy in electron volt? More specifically, it comes out in mega electron volt. Then you just substitute the value of C, square it, convert it into electron volt from joules, and because you want mega, you put 10 to the power 6 and all. The number that you get over here is 931. So the energy which is liberated by destroying one atomic mass unit, which is 1/12 the weight of the mass of carbon atom, will be 931 mega electron volt. So this is also obviously very important, and this is also very important. This is usually used in most of the problems. Now also remember that the mass of a proton is almost equal to the mass of the neutron, which is almost equal to atomic mass unit, but it is much larger than the mass of the electron. Electron's mass is negligible, but proton's, neutron's mass is roughly 1 AMU. Yes, it is roughly 1 atomic mass unit. Is that all okay, guys? Shall we proceed ahead? Yep, very good. Awesomeness, awesomeness. Buddy, we can discuss all your doubts towards the end of the class, or else the flow will get disturbed. Okay. Now, let's do some questions based on that. But before that, let's talk about binding energy and all of it. See, imagine you have some protons and you have some neutrons. All of them combined together inside the nucleus, and you have those protons, and of course you have those neutrons also. Okay, like this inside the nucleus. Here I will say Z number of protons will have a total mass of proton into Z. Here you have n number of neutrons. So the total mass will be mass of each neutron into n, which is the same as mass of each neutron into A minus Z. Usually A and Z are given to you, so A minus Z is n. Now if you add all these particles and combine them to give you an atom, you will see that there will be some energy which is released. That particular energy which is released is called as the binding energy, because I'm binding these people together. So there is some binding energy which is going to be released. And as per Einstein's equations, mass energy, if there is energy which is created, so some mass is destroyed. And that's exactly what happens. The nucleus has lesser mass as compared to its total total mass of isolated nucleons. Nucleons means nuclear particles. Protons and neutrons are nucleons. So if you take them separately, then if you weigh them, let's say for example, this is 4 kg, this is 5 kg. 4 plus 5 should be 9, right? But it won't be 9, it will be some 8.8 kg or something like that. So there is some mass which is destroyed. So because of that, I will say that there is a mass defect which is generally called delta M. This is called as the mass defect. This is called as the mass defect. And this particular mass defect is the difference of the masses. So if you take the total mass of the protons plus the total mass of the neutrons, which is Mn into A minus Z, this you subtract it with the mass of the mass of the nucleus, which is given to you, let's say, this will give you the mass defect. From this mass defect, you can obviously find the binding energy. So binding energy, the binding energy will be delta M multiplied by 931. Obviously, the unit will be mega electron volt, provided this is in atomic mass unit. This is an atomic mass unit. Is this absolutely clear what this equation is all about? Is this absolutely clear, my dear students? What is the mass defect? The difference of the masses, which is the mass which is being missing in the nucleus when all the particles come together. So there is some energy which is now created. That energy is mass which is destroyed into 931 mega electron volt. Keep this in mind. Let's do some questions. The energy equivalent of one atomic mass unit is how much? One atomic mass unit. I think I just did it. Come on, everybody should be able to answer it. Spam the answer right away right now, guys. Spam the answer right away right now. Come on, very, very laddu question. Yes, 931. I just did this right over here. If you have one atomic mass unit, the energy which will come out is 931 mega electron volt. If you substitute M as 1, E will be 931. Perfect. So the answer will be 931. Answer will be 931. Perfect. Let's see. If Mp and Mn are the masses of proton, neutron, element has a mass M, Z protons and neutrons, then the element has a mass M. That means the nucleus will have almost mass M. Come on. So what do you think? Who will be more, who will be less? I just told you that in the formation of the nucleus has lesser mass as compared to the total mass of the isolated nuclear particles. The total mass of the isolated nuclear particles. That means the mass of the nucleus is less than the total mass of this isolated nuclear particles. Yes, so that is why M is going to be less. Is this absolutely clear? Yep, C for Captain Shreyas again. Perfecto. 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 Very good. Very good. Awesomeness. Great. Great. Let's move. Let's move to the next question then. Let's move to the next question, guys. Here it is. Find the mass defect. The necessary atomic masses are given to you. Mass of neutron, mass of proton, and mass of oxygen. Okay. In this particular thing, I can see this is atomic mass number, this is atomic number. These things are given. So what will be the mass defect? We all know we should take the total mass of the proton plus total mass of the neutron minus mass of that particular atom, that is atomic mass defect. Mass of the proton. Mass of the proton. Each proton has 1.00727 units. But how many protons are there? 8 protons are there. Okay. This is what it is. Plus, what is the mass of neutron? So this is 16. So what will be number of neutrons, guys? 16 minus 8, which is again 8. Each neutron has a mass of 1.008665 into 8. Okay. Minus, what is the mass of that atom as a whole? 15.99493. That is it. So just have to do this now. Just see how much does it come out to be. Multiply and subtract, guys. Multiply and subtract. See what is that number that you get. Yep. You'll have to basically add these two. So it will be nothing but 1.00727 plus 1.0086665. The whole thing multiplied by 8 minus 15.99493. Just see guys, after solving, what is the answer that you are getting? What is the answer that you are getting? Yep. Is it 0.25, 1, 0.13, 0.05? Just see guys. See if you are getting the answer as C, which is 0.133, 0.133 atomic mass unit. Atomic mass unit. Just check this out. Excellent. C for Captain Shreyas again. Very good. Atluru, Krishna, Guru Prasad, Baswaraj, Dreams, Karthi. Great. Very good. Excellent. Excellent. Very nice. Now, next thing, we just saw that if you combine all the nuclear particles, then the energy released is binding energy. The reverse also holds true. If you give that binding energy to the nucleus, if you give that energy, you will break that nucleus into individual particles. Now think about it. If I give more binding energy, means I need more energy to break the nucleus. That means it is difficult to break that nucleus. That means the nucleus is more stable. Correct? But when we talk about nuclear stability, we talk about how much energy is required per nuclear particle. It's like, this is a happy family. Maybe some group of 5-6 friends. Group of 5-6 friends. Let's say there are 5 friends over here and you give 100 rupees and you give 100 rupees to them. So then if you give 100 rupees to them, they are very happy and they will split apart. Next time, imagine there are 10 friends in that circle. To them also you give 100 rupees only. You give 100 rupees only. If you give 100 rupees to these 10 friends, they also split apart. Now you'll be like, sir, I need the same money as a bribe to ask these friends, okay, now you are separate. Now you are not going to sit together. You are separate now. So cheap they are. So where do you think the friendship is stronger? Where do you think it is weaker? You might say, sir, both said 100 rupees. So it is the same only, sir. Both places the friendship is same. No, don't look at it like that. Check here. Per friend, per person, how much money does he get? 100 by 5. So that is 20 rupees per person. Here, 100 by 10, which is 10 rupees per person. So here the demand of each person is more. That means their bond is slightly stronger. So per person, they need 20 rupees. Here, per person, 10 rupees. Tata bye bye. All the friends are separate. Are you getting it? Are you getting it, my dear students? So what matters is to check the stability of the nucleus is never the binding energy, but it is always the binding energy per nuclear particle. So that is very, very important. So let me put over here the stability of the nucleus is given by the binding energy per nuclear particle. This is called binding energy per nucleon. Binding energy per nuclear particle or per nucleon. So when we did this particular question, if you multiply with 931 and divide it with the atomic mass number, you will get the binding energy per nucleon. As simple as that. So this is very, very important. The stability of a nucleus is given by binding energy per nucleon. Now there is a very interesting graph which comes. We'll come to that. There is a very interesting graph which comes over here. Observe this. On the horizontal axis, I will put atomic mass number, and over here binding energy, or maybe I can just put atomic number also, that's okay, which is the elements, and here binding energy per nucleon. This graph goes something like this. For different elements, it will go like that, and it reaches the maximum value and then it goes down like this. Yes, it goes down like this. It reaches a maximum value over here, and then you will see it goes down almost constant. This element is iron. The first element is hydrogen. Last elements that you get over here are uranium. Uranium. This is hydrogen. What does this tell you? Who is the most stable nucleus? Who is the most stable nucleus, guys? Think and tell me. Binding energy per nucleon quickly tells me the stability of the nucleus. So, iron is the most stable. This is very, very important. You should know this is the most stable element. No, most stable nucleus. I'm not talking about element or atom. I'm not talking about electronic configuration. I'm talking about the nucleus, most stable nucleus. Now, if this is the happiest person of all the periodic elements, what can you say about hydrogen and uranium? Uranium, hydrogen will be like, oh my God, I don't have anything. I have very low binding energy per nucleon. Uranium, understand, it has slightly better binding energy per nucleon, but not as better as iron. Not as better as iron. So, all these elements over here, they have lesser binding energy, but they would want to be stable. They are jealous. They are feeling J of iron. So, they would definitely want to reach over here. But in this process, what will happen? Their atomic number will become less. That means they will split into smaller elements. This is called as fission. This is called as fission. This is called as fission, guys. Yeah, very good. Similarly, hydrogen would want to become iron and it wants to combine the nucleus to go this way. They will fuse together. They will undergo fusion. Now you will be like, sir, so many hydrogen, so many helium, lithium. Sir, why don't they come together, sir? They can become iron, no, sir. They will become very stable, no, sir. What is the problem? Fine, the nucleus wants to be together, but these electrons are there. No, they are Kirik parties. They are Kirik parties. They will be like, no, boss, you cannot come so close. We will apply electric force of repulsion. So like it happens, no, in friendship also. Two friends wants to be together, but their groups are like they are rivals. In families also it happens. Like love marriage. Two families against each other. The boy and the girl love each other. Boy and the girl secretly they will meet. Oh my God, we will be together. We will have a baby. Okay, but their families full against. So it is like that. So hydrogen wants to be together. Fuse becomes very stable. But their families, their electrons, their relatives, they're like, no, you cannot come close. Got it? Understood the logic? Same thing. You'll be like, sir, uranium can become iron, no, sir. So big family is there. But very unstable. Too many politics. Very big family. They can split and become more stable. But that will not happen so easily. Why? The reason for that is, again, nuclear forces. There needs to be some driving. Like, okay, one big family is there. Okay, why to chumma fight? We have been together. Like that. Okay, let's continue. Let it go. We'll see later on. Unless somebody comes from outside, does some Kirik person comes. Villain type person comes and like, hey, you know what? This guy, full chadi he tells. Hey, this guy is this guy is this, oh, yo, God, full fighting, they will separate. So that fission reaction needs some external agent. That's what happens. Okay. Now, in any of these things, nuclear fusion or fission, let's say, for example, X plus, let's say we first talk about fusion. So X plus Y gives you Z plus some other things also can come. There might be some energy which comes out. There might be some energy which comes out because of the mass defect in fusion. Same thing can happen in fission also. In this process, maybe you can have some Z going into X and Y. This is fission. and there might be some energy which comes out over here. So in any case, these energies which are there, they are basically called as the Q value of that reaction. Q value of that reaction. And that Q value of that reaction is nothing but the mass defect into C square. This is provided you put everything in joules and this is in kg. But if you want it in atomic mass unit and all that, so delta M into 931. Obviously, this is in atomic mass unit and this is mega electron volt. The mass defect on both sides, these two and this one, there will be some difference of the mass. Usually, we can also write this as the binding energy of those products, whatever is there, minus product is this side, reactant is on the other side, binding energy of those reactants. That means here, these are the reactants. So this is the Q value. So if you keep this in mind, more than enough. Is that okay, guys? Everybody with me? Clear? Very good. Excellent. Yes. Q of the binding energy of the product minus binding energy of the reactant. Yeah, very good. Keep this in mind. Now, during the nuclear reactions where you have combining something, disintegrating something, etc., there might be some extra particles which come out. They are alpha, beta, and gamma particles. So let me tell you about that as well. So let's say there is an element X gets converted into element Y, and there is alpha particle. Then there is element X gets converted into element Y, and then there is negative beta particle, or sometimes you can have positive beta particle. Last time X star comes into X plus gamma. Now alpha particle is nothing but doubly ionized helium. This is beta negative. It is nothing but electron. This is beta positive, which is nothing but the positive version of the electron called as the positron. Looks exactly like that, behaves like that, just the positive charge. This is gamma radiation, gamma particle. This is nothing but electromagnetic wave. Gamma is like X-ray, ultraviolet, infrared. It's just a electromagnetic wave. So let me write down atomic mass number over here, and here, and also atomic number here, and here. So what happens in every case? When you have gamma radiation, then neither the atomic number changes nor the atomic mass number changes. It stays as it is, and whatever stays on the top, on the left hand side should be there on the right hand side. It should match the equality. Gamma particle does not have any atomic mass number, nor does it have any atomic number. It's a chargeless, massless particle. It's a photon, electromagnetic radiation. So A is A plus 0, Z is Z plus 0, RHS and LHS are matching perfectly okay. Similarly over here, alpha particle is having mass number of 4 and atomic number as 2. So mass number is 4. So to match it, this should have A minus 4. So A minus 4 plus 4 is A, and this at the bottom will have Z minus 2. Here, in case of beta particle, the charge is minus 1. So atomic number wise, it is negative 1. So this will be Z plus 1. So minus 1 if you do, it will again become Z. Every time the equality has to be maintained, LHS and RHS. Mass wise 0. So this will still be A. Here also same thing, this will be A, this will be 0, positron. Positron has positive 1 charge. So this will be then Z minus 1. So these are the nuclear reactions, guys. These are the nuclear reactions. Now, this beta negative and beta positive, they are basically just two particles which look similar. Everything is same except their charge. So it's said that in nature you always have the good, the bad, right? The positive, the negative. You have happiness, you have sadness. So everything comes in pairs. That is what this exactly tells us. Okay. So if there is a particle, there is, again, you can say an antiparticle. That's how it works. Nature is truly beautiful. Just like you have boys, you have girls. Yep. You cannot have only girls, you cannot have only boys. There is always coexist in nature. That's how nature has beautifully designed the entire system. Okay, now let's not get into uh, crazy things. I know in biology you study many crazy things, so we'll not get there. Anyways, coming back, in this process of beta particle emission, do you see protons have increased? And what does it come at the expense of? A neutron converts into proton. So here in beta decay, a neutron gets converted into a proton and a electron and an electron and an electron. Whereas over here, do you see a proton is becoming less? So you will see the proton gets converted into a neutron, and at the same time you will see a positron coming out. This is E plus, that was E minus, this was electron, this is positron. But in this process also what happens is there is another particle which comes over here. This is called antineutrino. Antineutrino. You should just remember this. Don't go into the details of it. They are quarks. They are smaller particles of the nucleus. And here you get neutrino. Those are the symbols. Neutrino has the symbol V or mu, you can say. This is neutrino. Neutrino. This V bar is antineutrino. So just remember these things. Just remember these things. They are just used for conserving mass, energy, momentum, everything. So these are some smaller particles, just like you have electrons, protons, neutrons. They are also there. Okay, great. All right, Nini, more Pandu Champa examples, they will come. Definitely. Everybody fine till this point? Okay. All right. Great. Great. All right. Cool. So let's do some questions coming up on your screen, and here it is. The binding energy per nucleon of dash and dash nuclei are 5.6 and 7.06 in the nuclear reaction. The value of Q energy of what and what exactly? I think something is missing, guys. Anyways, I will go to the next question. Something is missing over here. No worries. We'll just do the next question. Okay. So a nucleus with mass number 240 breaks into 120. Binding energy per nucleon is given for both of them. The total gain in binding energy in the process. Okay, let's understand the question. So there is a element X which breaks into mass number 120. So this is Y, this is 120. So there will be two such things, and there will be 240 over here. That is what is exactly happening. And it is clearly mentioned what is the binding energy per nucleon of X. So binding energy per nucleon unfragmented is 7.6 mega electron volt per nucleon. This is 8.5 mega electron volt per nucleon. In this process, there will be some change in the energy. So question is, how much is the change? Okay, one idea I have. If this is per nucleon, how much will be the total energy here? It will be 7.6. How many nuclear particles are there? 240. So this much mega electron volt is there on the left hand side, the reactant side. On the right hand side, 8.5 per nuclear particle. So there are 120 nuclear particles, but like that there are two nuclei. So into 2. Oh, now which is more, which is less? Obviously, this is more, this is less. So the question is, what is the difference of those binding energies? It will be 8.5 minus 7.6. This 120 into 2 is 240 only. So into 240. Is that right, my dear students? So this will be nothing but 0.9 multiplied by 240. How much will it come out to be? Yep, 216. Just check it out. Yes, perfect. 216. 24 into 9. It is just 24 into 9, guys. Or just 9 multiplied by 24. 10 into 24 is 240. So if you subtract 24, it will be 216. Correct. 216 mega electron volt. That is the answer. Everybody understood? So this was nothing but 8.5 multiplied by 240. And we just saw this is definitely more. So the difference of the binding energies is this bigger value minus this smaller value. So 8.5 minus 7.6 into 240. 240. That is the answer. Cool, guys. Shall we go ahead? Very good. Awesomeness. Awesomeness. Perfect. Let's go. Let's go to the next question coming up on your screen. The binding energy per nucleon of lithium and helium are 5.6 respectively in the lithium and helium is given. Okay. Respectively. What about hydrogen? Guys, I think again they have missed out some data. Sorry. Forget this. Some data they have missed out. No issues. Okay. Fusion reaction takes place at high temperature. Why do you think fusion reaction takes place at high temperature, guys? Why do you think fusion reaction takes place at a very high temperature? Two things. It's like two people, lovebirds, want to come together, but their families won't come together until you force them together. Why? Atoms get ionized, kinetic energy is high enough to overcome the Coulomb repulsion. Remember, I was just talking about the Coulomb repulsion. When the atoms try to come together, the charges will play a spoil sport. They'll be like, we will repel each other, electric force. So electric force will dominate them. They will not allow them to come together. So it is B, guys, I think. Yep, it is B only. So remember, at large distances, nuclear forces do not dominate. Electric forces dominate. So electric forces will repel them. Only when they come very close will they realize, oh my god, nuclear force is such a nice force. They will understand, oh my god, this girl is so nice. Oh my god, this boy is so nice. Why were we fighting? But they will not come and interact only. So that is the problem of love marriage. Got it? It is exactly like love marriage. Fusion is like love marriage. Two nuclei who love each other want to be together by nuclear force. But their relatives, their friends, or some social circles, that is their electric charges, they will repel. The electric force will be very, very large. They won't let them stay together. So only when they overcome their electronic repulsion will they be able to stay together. But for that, you need lot of force for them to come together, and you need lot of kinetic energy. Only then their love affair will be successful. Correct? Okay, perfect. Awesome. Very well, because of not skipping my recorded videos. Saeed, I'm so glad you did not miss my recorded classes. Okay, so we have come to semiconductors part. It is not going to take much. It's simple. We'll see all the important theory related to semiconductors, guys. First of all, in any solid that you have, there are energy levels, just like you have energy levels in atoms. Energy level of the first orbit, second orbit, third orbit, fourth orbit, etc. So similarly, when you have a solid, it's not a energy level, they are levels together. So this is very important. Oops. In a solid, there are energy levels, and these energy levels might look something like this. And in each energy level, you might have these electrons like this filling up. These electrons might be in that particular energy level. Okay, in that energy level. But these lines are so many number and so close that rather than showing them as distinct lines, we end up showing them like this. We end up showing them like this. We end up showing them like a energy band because there are so many lines. So we call it as an energy band. It's a band of energy, and inside of it, the electrons are there. Maybe it is completely there. So I will show it completely full. But what if, you know, you have you have let's say energy level. You have, let's say, energy levels like this. You have energy levels like this, for example, and the electrons are not there in all the levels. Maybe few levels only it is there, like this. Okay, like that, it is not completely full. Then when I draw the energy band, I won't show the energy band as full. It will show it like a partially filled container. This is how I'm going to show that energy band as. Is this clear? That energy band is partially filled. It is not full of electrons. It has more accommodating power. I hope this is clear. Now, in any particular solid, you will obviously have many such energy bands. So these are the energy bands like this. As you go higher and higher, the width of these energy bands becomes more. This is small, big, 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 big. Okay, something like this. Some of these energy bands might be completely full. Some of these energy bands might be completely full. And maybe after this, they are empty or something like that. The last full energy band is called as the valence band. This is called as the valence band. This partially empty or completely empty first band is then called as the conduction band. This is called as the conduction band. These are also conduction bands, but the first one is called conduction band. The last energy level, which is completely full, is called as the valence band. Why is this called conduction band? The reason for that is simple. If by chance this solid is connected to a battery like this in a circuit, then what will happen? It will be very easy to take out these electrons which are there in the conduction band. Why? Because these electrons are in a partially filled band. And remember, electronic configurations, Pauli's principle and all of that, if the orbit is half empty, it's easier to pluck out that electron. The electron orbits always try to maintain their completed states. They try to maintain their pairings and all of that. So if it is supposed to have 8 electrons, it would like to have 8 electrons. If it does not have 8, either it will try to gain 1 electron, capture it, or it will try to throw away those electrons. That's how it becomes stable orbit. So these unpaired electrons or these electrons which are not satisfying those orbits will be easy to pluck out. That's why they participate in conduction. That's why they participate in conduction. That's why they are called as conduction band. Is this absolutely clear? Now, usually they might be having a gap between them. So if you do not connect a battery, then at normal room temperature also the atoms will collide, and in the collision process these electrons will get energy due to thermal collision, and they can jump from one energy band to the higher energy band. So during thermal collision. So what matters over here is one more thing called as the band gap energy or forbidden gap, sometimes called as the forbidden energy band, forbidden energy band, or also called as the energy band gap. This plays a crucial role in deciding what kind of behavior that solid will exhibit. Is it a semiconductor or a non-conductor, or is it a fully good conductor? Okay, that is how it is. All right, this is the energy gap. Now, it so happens that when we talk about semiconductors, when we talk about semiconductors, how it looks, let me show you. Versus insulators versus conductors. This is valence band. This is conduction band. Valence band, conduction band, valence band, conduction band. So guys, let's say here what happens is this is conduction band partially filled and valence band completely filled. They will overlap each other. There is overlapping. Here there is no overlapping, but there is some gap. Here there is no overlapping, but the gap is even more. So this is very important. When this energy gap is much larger than the thermal energy K into T. Do you remember K? Boltzmann constant. This is your Boltzmann constant. If you remember, energy which is involved in thermal collision is in the order of kT. Kinetic energy of a gas molecule, half kT, 3 by 2 kT, 5 by 2 kT, like that. So imagine the thermal energy is in some kT order of values, 10 to the power minus 23 into the temperature. Obviously, that is the only amount of energy which can be involved in the collision process, which can transfer the electron to a higher orbit. So if the band gap is much larger than kT, then what will happen? This electron can never ever get energy due to collision and make a jump into the conduction band. Can never ever make a jump into the conduction band. Is that absolutely clear, my dear students? It can never ever make a jump into the conduction band. That means this conduction band, if it was empty, obviously this would be an insulator, because even at room temperature, that energy won't be sufficient to bring the electrons over here. Absolutely clear, my dear students? Absolutely clear, everybody? Okay. But imagine this particular scenario. This is completely empty. Here, this particular energy gap is in the order of kT, in the range of some few electron volts. So when you give that thermal energy, these electrons will be able to jump into the conduction band, thereby exhibiting conductivity. So these kind of devices then are called semiconductors. They are called semiconductors. The exact opposite will be over here, where already they are present in the conduction band. So you don't have to give any energy. They are already present in the conduction band. So they are then called conductors. One major difference between conductors and semiconductors, apart from the band gap, is that here, in the case of conductors, if you increase the temperature, then resistance will increase. Whereas in semiconductors, if you increase the temperature, then the resistance will decrease. In case of conductors, voltage is proportional to current. That means it follows Ohm's law. Here, the voltage is not proportional to the current. That means it is going to behave in the non-ohmic format. It is not a linear graph, it is non-linear graph. All these are important things. Is this absolutely clear, everyone? Very good. Awesomeness. Shall we go ahead? Guys? Excellente. Excellente. Now, there is a very interesting thing which happens in a semiconductor, which is, say for example, guys, we are taking these two bands and this is full of electrons. What happens is, due to the thermal energy, these electrons make a jump. So, due to the thermal energy, they are making a jump where? Into the conduction band from the valence band. The moment they make a jump, what happens is there is a vacancy which is created. There is some vacancy which is created. And that same vacancy is because of the loss of the electron. The electrons are now over here. They have left it. It's like there is a void, like some Champa left Pandu. There is a void in Pandu's heart. There is a void in Pandu's heart. This void is because of the loss of the electron, often called, this is often called, this particular void over here, this is called as the hole, and the ones over here where the electrons are, they are called as the electrons. Obviously, they are electrons, nothing else. This is electron, this is loss of the electron, there is a void that is called as hole. So hole can be treated just like electron is negatively charged. Hole, I can say it is the loss of electrons, so positively charged. Agree, disagree? Now, what happens when you have a semiconductor solid? This is very important now. When you have a semiconducting solid, this is the solid of semiconductor. See what happens. Very, very important, guys. Very, very important. This is a pure semiconductor. This is also called as intrinsic. Intrinsic means pure semiconductor. There is nothing else. Example like silicon semiconductor, germanium semiconductor, like that. Pure germanium atoms, pure silicon atoms. There will be, due to thermal collisions, electrons everywhere, electrons scattered across everywhere like this, and an equal amount of vacancies over here, equal amount of vacancies over here, which are holes. Agree, disagree, and they will be randomly formed by thermal energy. Okay. Now, if the temperature increases, what will happen? What will happen? Think about it. If temperature increases, then the electron hole pairs will also increase. Then the number of electrons and the number of holes which are there, their pairs will also increase because more vacancies will be created. Keep that in mind. Now let's say you connect this to a battery. This is positive terminal, this is negative terminal. What will happen? Positive will repel the holes. So the holes will begin to go like this. The electrons will get attracted by the positive or get repelled by the negative. They will go like this. The holes moving this way will create a current of the hole. So this is current of the holes. The electrons going this way, negative going this way is like positive going the other way. That means the electrons also create a current in this way. So this is the current due to the electron. So because of that, I can say there is a net current in the circuit. I can say there is a net, this is the net current in the circuit. And this net current is nothing but the addition of the hole current and also the electron current. This is another very important equation. The net current is the addition of the hole current and the uh, electron current. Perfect, everybody? Okay. Now there is also an additional formula which you might have learned about conductivity. Conductivity, try to remember conductivity. Conductivity is sigma, which is n into mobility into drift velocity. Just remember this. This was conductivity, which was n, which is number of charges per unit volume. This mu was mobility. This was mobility. If you forgot mobility, what it was, yeah, it was drift speed per, it was nothing but your drift speed per electric field, and this is not Vd, so sorry, this was charge. All right. Into Q. This is how much charge are you carrying. This is very, very important formula. Nu into Q. Mu is mobility, which is drift speed per electric field. Q is the charge which is being carried. This is the conductivity in conductors. But for semiconductors, notice how the formula becomes. It will be the addition of conductivity of holes plus conductivity of electrons. So the total conductivity becomes, for holes, it is nothing but how many number of holes are there per unit volume into the mobility of the holes into the charges of the holes, which is E, plus again over here number of electrons which are there per unit volume into mobility of electrons into the charge of the electrons, which is again E. So this is a very important formula for conductivity of semiconductor. What is this formula for? Conductivity of a semiconductor. Now, if it is an intrinsic semiconductor like silicon, germanium, etc., you will see that the number of holes which are there and the number of electrons which are there, they are equal in amount, and that is then called as intrinsic semiconductor concentration. What is this? Ni, intrinsic semiconductor concentration. Intrinsic semiconductor or intrinsic concentration. Intrinsic concentration, Ni. Very, very important. All right, guys, all these parameters, will you remember, yes or no, or you will forget? Cool. Okay. Now, is there something like an extrinsic semiconductor? The answer for that is yes. Say, for example, these are your energy bands. And this is that semiconductor solid. Okay. Say you add some impurity to it. So they will then become semiconductors which are extrinsic in nature. Externally, you have done something extrinsic in nature. And in this extrinsic semiconductor, let's say there are more electrons as compared to the number of holes. So I will say Ne is larger than the number of holes. This can be achieved by adding impurities, which are called as, this is pentavalent atoms, which are basically donor in nature. What do they donate? Electrons. They then become N type of semiconductor. When N means negative, means electrons are more in number. That leads to an additional band which is formed over here with an electron band over here. This is that donor impurity. Remember that this was your original valence band and this was your conduction band. Earlier, the electrons had to jump from here to here. Now you are helping them by providing additional electrons which only have to jump from here to here. So it is easier for them to jump as compared to this, which is hard. Therefore, this increases conductivity. What does it increase? It increases conductivity. Sigma. It increases conductivity. Everybody clear till this point? Very good. Awesome. Usually pentavalent atoms like phosphorus. phosphorus. Phosphorus usually are used. The exact opposite is when you have more holes, more vacancies as compared to the number of electrons. So in this case, number of electrons is less as compared to the number of holes. This then comes because of usually trivalent atoms. They have only three electrons in their outermost orbit, trivalent, 3 electrons, and they are then called acceptor. They are called acceptor elements, and they produce nothing but P type of semiconductor, which is extrinsic in nature. Examples are aluminum. Aluminum, yes, they are acceptor. So it creates a vacant band over here like this. And what happens is, this was your conduction band, this was valence band, this is your acceptor band, which is there. So earlier, the electrons had to jump from here to here. Now they don't have to jump so high. It will be much easier for them. This was harder. So again, you have increased the conductivity. Increased the conductivity. Is this absolutely clear, everyone? Very good. Now, in any case, Ne more than NH or NH more than Ne, you will notice one important formula, that NH multiplied by Ne is always going to be, remember this Ni, intrinsic concentration when both were equal. So that will be always equal to Ni square. This is again a very important formula. NH into Ne is equal to Ni square. This is valid for both N type as well as P type of semiconductors. Okay, guys, till this point clear? If they are given ideal diode, then it has no resistance. Yes, it has no resistance. Correct. Very good. Cool. So let's do some questions based on this. Let's do some questions based on this. What is it? If the temperature increases, the electrical resistance will. If the temperature increases, the electrical resistance will what? Come on, guys. Very simple. If the temperature increases, what will happen? The resistance will increase for conductor, but for semiconductor, it will reduce. Yes, we just saw that. It will increase for conductor, but reduce for semiconductor. I just told you over here. When temperature increases, resistance increases for conductors, but for semiconductor, resistance will decrease. I just told you this. Correct? Yep, very good. Awesome. That was C option. Moving on to the next one. The forbidden energy, that means the band gap energy between valence and conduction band for conductor, semiconductor and insulator, Eg1, Eg2, Eg3. Conductors, it will be the least, no? For conductors, Eg1 will be minimum. For insulator, this will be maximum. For this semiconductors, this will be in between both of them. In between both of them. Correct? So what should be the correct answer, guys? Come on. Yep, very good. Very good. EG1 is minimum, EG2 in between, EG3 maximum. I think B option should be correct. Yes, B option is correct. Very good, Guru Baswaraj, Srinivas. Awesomeness, awesomeness. Great. Now let's go to the next point, which is the semiconductor diode. We'll see this working and then we have applications. It's not going to take us much time. Now imagine you bring P type and N type together. Oh, by the way, before I forget, this question is also very important. P type semiconductor is neutral or positively charged or negatively charged? Answer it in the chat box. Let me see how many of you can get it. P type semiconductor. Is it positively charged or negatively charged or neutral? Very, very important. By the way, this is valid for P and N type both. Also, one more important point, P and N type both are electrically, both are electrically always going to be neutral. This is very important. I know many people feel P type is positive, N type is negative. Let me explain why. See, a lot of people think, sir, extra electrons have come. Why? Because in that outermost orbit, something like phosphorus. So instead of 4 electrons, fifth electron has come. So it will become negatively charged. Think for a moment, yes, that electron is available for conducting, but did you forget deep inside the nucleus, there is one extra proton which will come because the element has changed to phosphorus. So that extra proton will compensate the net charge of the solid. So the total charge of the solid is never positive or negative. Same way, if it is aluminum, yes, one electron is less. Does not mean it is positive. Yeah, it is positive in that region, but as a whole, solid inside the nucleus, there is one less positive charge also, which is one less proton. So as a whole, the atom is electrically neutral. Understand that. So it is always going to be electrically neutral. Keep that in mind. Is that absolutely clear? The difference happens when you connect P and N type, both of them together. When you have this P type, this is your P type, and this is your N type, both of them together. So what happens in N type? There are more electrons. Yes, there are holes also, but the holes are less. In P type, obviously, the holes are more. Electrons are there, but they are very less. Maybe some here, there. Here also, somewhere one or two holes will be there, but it is very less. This is a PN junction. Okay. Now, imagine this. You let this happen. These are like, just imagine these are Pandus in the N type. Okay, let's take P for Pandu. And this is Champa. So P for Pandu, N for Champa or Natasha, some random girl. I hope there is no Natasha in the chat box right now. Okay. So P for Pandu, N for Natasha is there. Now, these are like boys' hostel Pandus. These are like girls' hostel. They have never seen each other. These Pandus see beautiful Natashas. These Natashas see very handsome Pandus. What will happen? Immediately they will start dating each other. Getting my point? So these Pandus immediately will start meeting these Natashas over here. Oh, what a beautiful Natasha. 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 Like that. They'll start going like that. Understood? This process of meeting each other, they are called as diffusion. What are they called? Diffusion. So the majority charges, what do they undergo? Diffusion. They undergo diffusion. Now, in this process of diffusion, what exactly happens? Because the holes go here, and obviously the electrons might go on the other side. You can look at it the other way also, or you can think of it, Champa's over here or the Natasha's over here went here. Anything, guys. Why only boys should go? Maybe the girls will go. Okay. So in this process, what will happen is, in this process of diffusion, because of it, you will see the electrons have gone here. So this will become negatively charged actually, and this will then become positively charged. This will then become positively charged. Yes, this will become positively charged. So there will be a charge on the N which will be positive. There will be a charge on the P which will be negative. So there will be a voltage difference. In fact, there will be also electric field between them from positive to negative. There will be an electric field like this. There will be an electric field which will be in this direction. And in this process, because negatives have gone there, positives have gone here, there will be a current which will be going which way? Like this. Correct? Positive went here, negative went here. So positivity has gone towards the N side. So this current is called as the diffusion current. What is it called? Diffusion current, because the charges have moved. So there is a diffusion current. Current which is diffused is called as diffusion current. There is also electric field, and therefore there is high potential here, high potential here. There is low potential here. This difference is called as the potential barrier. What is this called? Potential barrier. This is called as the potential barrier, and this truly acts like a barrier. Why does it truly act like a barrier? Understand that. Now just imagine, guys, this positives and negatives have come here. This positives and negatives have come here. Papa, this positive charge says, I want to go here. This Pandu says, I want to go meet this Natasha. Just imagine what will happen to this Pandu when he says, I want to go meet this Natasha. This electric field will say, I will apply a force on you, like this. Because electric field is there, potential difference is there. This Pandu will be asked, okay, you want to go meet Natasha? There is a barrier. Barrier means obstruction, wall. I have built a wall. You have to jump over the wall and then go meet Natasha. Pandu will be like, oh, yo, such a big wall. I can't jump. Sorry, it's okay. I will stay here only. If by chance it has lot of energy, this Pandu, then he will be able to jump. So there is a barrier which is created. Who created this barrier? Those Pandus who met those Natashas before, now they are in relationships. So remember, these Pandus went here, Natashas went here. So because of that, relationships happened. Those couples are telling those other singles that, listen, you can't go there. I have made a wall. I have made a wall. I am in a relationship now. You go to hell. If you want to go meet that Natasha, you climb that wall and go. So that's it. Gone. Understood, guys? This region in which the potential barrier is created, that is also called as the depletion zone. That is also called as the depletion zone. Very, very important. Now, there is one very interesting thing which happens in that particular depletion zone. We will talk about it now. Observe carefully. Now, see, guys, very important. Observe. So, this side became positive. This side became negative. Now, even in the P side and even in the N side, there will be obviously some holes here. There will be some electrons even on the P side. I know these electrons will be less in number in P and these holes will be less in number on the N side. These are your minority charge carriers. Now, because of that electric field, think what will happen. This electron will experience a force here. This positive charge will experience a force here. So this hole will go like this. This hole will go like this. Whereas this electron will go like this. This electron will go like this. Positivity going here, negativity going there means effectively positivity is going this side. So this is the direction in which current is set up. This process is called as drifting. And this drifting involves whom? Minority charge carriers. Minority charge carriers. Minority means in p-type, electrons were very less. They are involved. In n-type, holes were very less. They are involved. That's why minority charge carriers. This current is then called as the drift current. This current is then called as the drift current. Is this absolutely clear, guys? Okay, very good. Very good. Awesome. Awesome. Great. I think this part will come in the shorts. Which part, guys? Oh, the Natasha part. Oh, definitely. I hope. Okay. Now, if you consider both the drift current and the diffusion current together, now see guys, if it is a unbiased PN junction, unbiased means some teachers are there, whether topper, backbencher, boy, girl, this, that, doesn't matter. You have done a mistake, punishment. You have done very nice, very good, claps. But some teachers are biased, meaning, yo, my front bencher, my pet student, every day my pet student gets one bottle of water for me. Miss, sir, please, sir, take water, sir. Full marks, even though he does not write anything, even though he writes some gibberish, teacher will be like, oh, yo, papa, I'll give 2 marks extra. But one student will be there, sometimes very smart also, always full country fellow. That's it. No matter what he does, you get out of the class. You -1 mark. You do this. Call your parents. Always. So biased versus unbiased. Got it? Okay. So this is unbiased. So you will see in such a thing, there will be a diffusion current like this, diffusion current like this, and there will be a drift current like this. So guys, tell me as a whole, what will be the net current? So the net current will be 0. Makes sense. Net current will be obviously 0. But let's say second scenario. Now what I do, P I connected to positive terminal, N I connected to negative. Here, P I connect to negative, N I connect to positive. These are unbiased. Sorry, these are biased now. This is now called as reverse biased. Reverse bias, because P to negative, N to positive. This is forward bias. This is forward biased. These are no longer unbiased. Unbiased means nothing was connected. So the voltage difference is basically 0. No voltage, now positive, negative. You will see in forward bias, the drift current will not change. The drift current is still the same, almost, not much of the difference, but it is the diffusion current which increases. It is the diffusion current which increases, because of which there will be a net current like this. There will be a net current in this direction from P to N within the diode. But in reverse bias, you will see the diffusion does not change. The diffusion is almost the same as before when it was unbiased. It is the drift current which reduces. The drift current will reduce, because of which there is a very small current which will go in the opposite direction. This is a leakage current because it is very small. It is called as leakage current, which is negligible. Negligible. So that is reverse biased. So this tells me that a PN junction acts like a diode. Diode means one way. If you forward bias it, it allows full current, but in reverse bias, it does not allow much of a current. It does not allow much of a current. Relatable, Karthi said. Oh, dreams, looks like you have faced biasing. Okay. Okay. Now, if you take the voltage versus the current graph, very, very important graph. This is, sorry, this is the current. This is the voltage. This is 0. If I am on this side, it is forward because voltage is a positive, forward bias. If I'm on this side, obviously it is reverse bias. How does the graph look like? Observe carefully. Initially, when there is no voltage, there is no current, but in the forward bias, when you start applying voltage, the current slowly increases, and there comes a point where the current ends up overcoming this potential barrier which was there. So once that barrier is overcome, that means imagine your forward biasing, that wall which was there, that wall gets broken, and there is a sudden surge of Pandus trying to meet Natasha's. So you will see that initially Pandus will try to overcome that barrier, but then there is a sudden surge and it will go like this. So this point where it happens is called as the knee voltage. Knee voltage, where you overcome the potential barrier. Here, as you can see, the voltage is definitely not proportional to current. So it is definitely non-ohmic. And you can see one more thing over here. If you take any point, any if you take any random point and any random point here, this is the voltage, this is the current. If you take the resistance, which is voltage by current, this will obviously not be constant, because here it is different, here it is different, it is not a straight line. There is one more term which is defined over here, which is called dynamic resistance. Dynamic resistance, it is not voltage by current, it is change of voltage by change of current. Very, very important. So maybe if the voltage changes by some amount, the current changes by some amount, so then this will be delta V. It's like the slope, and this will be nothing but delta I. So that is called dynamic current. Sometimes some questions can come in that. In the reverse bias, what happens is, we just saw that the drift current reduces. So there is a small difference which is called as the leakage current. So there is a small current which goes, negligible it is. This is obviously the leakage which is happening until you overcome something called as the breakdown, and then there is an avalanche. Avalanche is like a big block of ice melting and coming down. So there is an avalanche, breakdown which happens. Avalanche breakdown which happens like this. And in this case, when that avalanche breakdown happens, the voltage is going to be constant. Even if the current changes, see, if the current changes along the y-axis, the voltage does not change. This happens in the reverse bias. Reverse breakdown, it is also called. Avalanche breakdown. All these things. Yes, logic gets Chependi. Definitely. Okay. Awesome. Jan 2025 Prakritik. So glad. Yep. Great. So all these things you should know, guys. And now let's see some questions on that. The barrier potential of a PN junction depends on, come on, let's do this. The barrier potential of a PN junction. Type of semiconductor, definitely. Amount of doping, yes. Temperature, yes. All three of them, definitely. If temperature is different, voltage will be different, because more electrons or less electrons will transit. Amount of doping means more electrons, less electrons. Semiconductor, what a semiconductor it is will decide how many Natasha's Pandus will transit. Definitely, all three of them. Electron concentration in N-type is the same as the whole concentration in P-type. External field is applied on each of them. Compare the currents. This is very interesting. Come on, guys. This is very interesting. You might think, sir, electrons are more in N-type. In P-type, holes are more. What if the amount by which holes are more is same as the amount by which electrons are more in N-type? So you might think the conductivity will be same, but the answer is no. You will see the current in N-type is more than the current in P-type. What is the reason for that? Let me go back over here and tell you. The reason for that is this. Even though both these terms look similar, and in intrinsic, NH and Ne might be equal also in intrinsic only. E is also same, which is the charge. Mu is not the same. Usually, you will see the mobility of holes is much, much lesser as compared to the mobility of electrons. That means electrons can move easily, whereas holes, if they have to shift their place, it's difficult because they are vacancies. So mobility of electrons is more. That's why conductivity of electrons is more. That's why the current of electrons is usually higher than the current of holes. That is the logic behind it. Is that okay? Very, very crucial. So that is why current in n-type is more than p-type, is only based on the mobility. Yes, mobility. Very good. Very good. Let's move to the next question. Electron concentration is given, hole concentration is given. What kind of semiconductor is that? This is very simple. This is very simple, guys. Come on. Yeah, what is it? It's definitely more electrons are there. So it is N type of semiconductor. Very nice. Great. So PN junction, forward bias, reverse bias, guys. One thing, symbol you should know. If this is PN, so P will have the vertex of the triangle with this. This is the symbol of a PN junction diode. Yeah, this is basically, sorry, my bad. I wrote it exactly opposite. The direction in which the current will go. This is the symbol of a PN junction diode. This is P type, this is N type. Okay, so you should know the PN junction diode, very, very important. So if the current goes like this is forward bias. If the current goes like that, tries to, that is reverse bias. If there is an ideal diode, if the diode is ideal, please keep in mind the voltage difference is 0 volt. But if it is a silicon diode, silicon diode, silicon, S for silicon, S for 7, 0.7 volt is the voltage difference. If it is a germanium diode, usually the voltage difference is 0.3 volts. This is something which you should remember. Okay, clear, guys? Very nice. Let's do some questions. Consider the junction as ideal, PN junction. What is the value of the current? If it is an ideal junction, that means there should be 0 volts. There is one resistance and there is voltage difference across this entire thing, which is 4 minus 6, which is 10 volts. So the current will be voltage by resistance, which is 10 by 1 kilo, which is 10 to the power 3, which is 10 to the power minus 2 amperes. 10 raised to minus 2 amperes is the D option. Very easy peasy lemon squeezy. Okay. Not just silicon and germanium, any diode will not conduct in reverse bias. Not just that, any diode. I just told you that over here, right? Why they will not conduct? Because the drift current is going to be smaller and the diffusion. Sorry, guys, I made a mistake here. So sorry. So sorry. I'm just correcting it. Please redo. So sorry. The drift current does not reduce. My bad. Sorry. The drift current remains the same. It is the diffusion current which will reduce. The diffusion current will reduce. So the balance will be the leakage current. So there is a very small difference, and that is the reason why that reverse bias current will come, which is very, very small. Okay. Is that okay? I just made that change. Please correct it. Please correct it. Okay. Very, very important. Next one. If there are diodes connected as shown, the current flowing in the resistance R1 will be the current flowing through resistance R1 will be. Now see, guys, this is the positive terminal, this is negative. So obviously there will be no current here because there will be reverse bias. P is connected to negative, N is connected to positive. Here it will flow because this diode will be forward bias. So if at all any current is going, it will go like this, like this, like this, like this, like this, and like this. In this entire path, the total voltage by total resistance, check it out. The only battery which is there is 10. All the diodes are ideal, so no drop. 2, 2, only 2 ohms resistance are there. So 10 by 4, which is 5 by 2, which is 2.5 amperes. 2.5 amperes is option A. That's it. Why is this reverse? Because positive is connected to the N type. So that will be non-conducting diode. Is that okay, everyone? Very good. Excellent. Awesome. Awesome. Now there are multiple applications of diode. Diodes as rectifiers means rectifier is a process by which you convert alternating current to direct current, and you have the use of a single diode which is connected to a AC circuit. Then you will notice the output that you get if the AC signal is like this. If the AC signal is like this, the output that you will get will look like this. This is the output that you will get if there is a single diode, because only in the forward bias the diode will conduct. When the negative cycle will go on, the diode will be reverse bias, it will not conduct. This is called as a half wave rectifier. Half wave rectifier. Similarly, if somebody uses two diodes, something like this, using something called as a center tap transformer and all of that. Yep. So you need something called as a center tap transformer and all of that. So this is what it is. So here again, on the input side, you are giving AC signal. This is your AC signal. This is your output. In the positive cycle, this diode will be forward bias. In the negative cycle, this diode will be forward bias. Through this resistor, every time the current flows in the same direction, both the positive and the negative cycles, there will be some diode which is forward bias. So it has now converted into a unidirectional current, which is direct current. This is called, because the entire wave has been rectified, it is called as a full wave rectifier. It is called as a full wave rectifier. Keep this in mind. Some questions on that. If a PN junction, a square signal of 10 volt is applied, as shown, the output will be how? How will the output be? Check this out. When you give this voltage, negative 5 volts, this is negative as compared to, sorry, this is negative because you are giving negative 5 volts. So, because this is negative 5 volts, this will be 0 volts with respect to that. So, this is lower potential, this is higher potential. So, this will be reverse bias. So, no current will go. If the no current will go, no drop will be there across the across the diode. So, what will be the voltage? What will be the voltage that you will be getting? No current is there. If the current is 0, what will be the voltage, guys? Remember the output voltage will be the current multiplied by the resistance. If there is no current, there is no voltage, so the voltage will be 0. 100% you will get 0 volts. 0 volts. So you should start off with 0 volts initially. So this is, let's say for example 0, this is 0, that is also 0, 0. Okay, fair enough. Now when the voltage becomes 5 volts suddenly, when the voltage becomes plus 5 volts as compared to this 0 volt, this will now become forward bias. Current will start to go, and when current is there, what will be the voltage? It will be I into R, and all that voltage which is there here will be also here, which will be roughly 5 volts, Okay. So what do you think will happen, guys? Yes, what do you think will happen? you will see a voltage of 5 volts here. Earlier, it will be 0 volts. It will be 0 volts. Yeah. So I think it should be D option. Yes, it is D option. That is the answer. Yep. Very nice. Moving on. Next question. If there is a half wave rectifier, which one of the following waveforms is true for voltage across CD? Voltage across C to D. Come on, guys. This is half wave rectifier. Half wave rectifier. It cannot show full waves. So one option at least gets eliminated. This is a full wave rectification. What is this nonsense? This will not happen for sure. Okay. Diode will conduct initially, and if input is positive, the output will also be positive, then nothing will be there, then positive. So forward bias, reverse bias, reverse bias. So I think the graph which will be correct will be B option. Check this out. Yes, B option is the correct option. Very good. B option is correct, everybody. Very nice. Very nice. Excellent. Great. Now, yeah, let's see all those things related to LED, photodiode, etc. I'll just give you the basic things which are important. See, if you have a diode which gives out light when you pass current in forward bias, that is called as a light emitting diode. What is it called? Light emitting diode. It happens because of the combination of electrons and holes, and it emits energy in the form of photons. The exact reverse is when you have a diode on which, when light falls, the conductivity change, and that is called as a photodiode. Photodiode, and always a photodiode is operated in reverse bias. When light falls, the conductivity change, and thereby you can understand how much light is falling. The next type of diode is which is always used in reverse bias, that too in the breakdown region. That is called as the Zener diode. Zener diode. This is used in the reverse breakdown voltage. Reverse breakdown voltage. And this is used for voltage regulation. Voltage regulation. What is this used for? Voltage regulation. Is this clear, guys? Everybody? Perfect. Awesome. Great. All right. All right. Cool. Very good. Very good. Now, let's jump to basically our, what do you say? Logic gates. Let's jump to logic gates now. That is the last part, okay, of this particular thing. So, every machine understands not human language but the machine level language, which is always in the form of zeros and ones or highs and lows. So 0, 1, or false, true, no, yes, 0 volt, 5 volt, low, high. This is how machines understand. This is your machine level language, which is also called as binary. Binary. Bi means two. So this is your machine language. This is your machine language. And everything that you see, artificial intelligence, machine learning, this, that, website, browser, mobile app, everything works on zeros and ones. Anything, your video, your audio, your pictures, writing, email, calls, everything works on zeros and ones in phones, mobiles, everything. Awesome. Great. Now, when these operations are performed, obviously, there are some basic operations which are performed. Like when you learn integration, what is integration? Summation means addition. So you learned addition back in the second grade. So this machine level language has some basic operations. What are they called? Let's talk about it. The first one is basically called as the NOT operation. NOT operation. The symbol for that is, if Y is the output, X is the input, or let's say A is the input, then A bar is the NOT operation. That means whatever you give, it will be exactly opposite. So just to give you an example over here, the symbol for that is something like this. This is not a diode. You see a triangle with a circle, not a line. So let's say this is input and let's say this is output. So if the input is 0, the output is high or 1. If the input is high, the output is low or basically 0. Exactly inverted. That is called as a NOT gate. Gate means that operator. This is a NOT gate. Similarly, you have AND operation. AND operation. AND operation is represented as A dot B. The symbol for that is a D. That's all. A and D, D, that D symbol. There is also NAND operation. NAND, which is Y is A dot B. This is AND, the negation of that. Meaning, whatever output you get from the AND gate, you negate it. You put a NOT gate in front of it. That is a NAND gate. Let me show you by example. Let's make something called as the truth table, which explores all the possibilities. So this is the AND, this is the NAND possibility. So let's see what will that outputs exactly be. Possibilities are both are false, one is true, both are true. 0 and 0 is always 0. 0 and 1, both of them are not 1, only one is 1. So then the answer is 0 still. If both are true only, then it is true. This is also 0, this is 1. NAND is exactly opposite. So this is 1, this is 1, this is 1, and this is 0. Keep this in mind. Everybody, absolutely clear? Very good. Okay, awesomeness. Now please remember, there is a extension of this, which you will see. This is nothing but A plus B separately bar. This plus you will see later on is a OR operator, OR. So A dot B whole bar is A bar plus B bar separate. What is that plus? We will see now. That is called as the OR operation. OR gate means the output is input plus out input, and the symbol for that is a curved D, something like this. You also have NOR gate. Yep. So this is Y is A plus B, the whole bar. So it's just that same OR gate with a NOT gate in front. Let's understand it with a truth table. Inputs are there. Output is OR, or let's say NOR. What is this going to be? Okay. 0, 0, 0, 1, 1, 0, 1, 1. 0 or 0, nothing is 1. 0 or 1, one of them is 1. Enough. 1 or 0, 1. 1 or 1, 1. Any one is 1 or high or true, it is true. NOR will be exactly opposite, so just negate it. That is what the answer will be. This is a NOR gate. Obviously, this can be also written down as A bar dot B bar. You are separating that common bar into separate. Plus becomes dot. Here, that dot becomes plus. Also keep in mind one interesting thing, that if by chance you have a NAND gate whose inputs are shorted, that means you are connecting it, then if you short it, then it is exactly a NOT gate. Yeah, it behaves like a NOT gate. A NAND gate which is shorted, that means both the inputs are the same, it behaves like a NOT gate. Same thing is also true for a NOR gate, meaning if the inputs are shorted for a NOR gate, it behaves like a NOT gate. You short means connect the terminals of the inputs here. It behaves like a NOT gate. Very, very important again. Okay. The last thing over here, sometimes it might come exclusively OR gate, XOR. Output is A plus with a circle B. Symbol for that is like a OR gate only, but you put these double curved lines. That is a XOR gate. How does it look? Truth table wise, this is AB. This is your XOR. Observe now. 0, 0, 0, 1, 1, 0, 1, 1. Exclusive OR means either one is true, not both. 0 or 0, 0. One of them is true, yes. One of them is true, yes. Both are true, false. Exclusively one should be true. That is called XOR gate. As simple as that. Perfect. Very good. So these are the basic gates, and let's see some questions on that. What is the correct equivalent gate? What is the correct equivalent gate? Oh, by the way, NAND gate, NOR gate are called universal gates because using NAND and using NOR, you can make any gate, NOT gate, OR gate, XOR gate, anything. So that's why NAND gate and NOR gate are called as universal gates. Just study it and keep Manu XOR just in case. Okay, first things first, can you see this is a NOR gate which is shorted? So what happens? It behaves like a NOT gate. Two NOTs, one after the other, this one and this one, this one and this one. What will it behave like? It will behave like a simple wire. Nothing will be there. So that's it. Only this gate is there. What is this particular gate, guys? This is a NOR gate. This is a curved line with a circle over here. So definitely it is a NOR gate. Okay? NOR gate. Is that understood, everyone? Is that understood, everyone? Very good. Awesomeness. Proud of you. Next question, guys. Which logic gate is represented by the following combination? Which logic gate is this now? Come on. See which simplified version does it become? Okay. So first of all, if this is A, this is A bar. If this is B, this is B bar. This is a OR gate, and then there is a NOT operation. Okay, fair enough. So OR operation means A bar and B bar. OR means plus, and then finally that NOT. I know what I can do. I know what I can do. Just think about it. This and this are added together. Okay, and then knotted. So separate those things. So write A bar separate, write B bar separate. Okay. And if there was a plus, make it into a dot, and that common bar, separate it out eventually. This rule I have just showed it to you over here. This rule I just showed it to you over here. Yeah. Where did it go? Here. A plus B whole bar is A bar dot B bar. Or even this, A dot B whole bar is A bar plus B bar. Okay. So therefore, what I can do, I can separate it out. What is A bar bar? It is A. What is B bar bar? That is B. What is A dot B? It is a AND gate. So it should be a AND gate, which is option A. Perfect. So simple it is using those rules, or else it becomes little bit tricky. Becomes little bit tricky. Correct. It is AND gate, not B option. Okay, be careful. Dot is AND, plus is OR. Yeah. Okay, great. Next one. This was NEET 2018 question. Which operation is there in this particular thing? This is A, this is B bar. A is coming here, this will be A bar. B is coming over here. This is AND. So A dot B bar. This is A bar dot B. This is OR gate. So OR means plus. So A dot B bar, OR means plus. A bar dot B. Where is it? I think B option. Yes, B option is the right answer. Very simple. OR means plus, AND means dot. Excellent. Very nice. And there we come to the end of the class. Now, first of all, tell me, did you love the session or not? And if you loved the session, not only put it in the live chats, I want every student attending live or recorded mentioning you loved it or liked it. Yes, sir, I learned a lot. Yes, sir, I understood a lot of things. And I want your full attendance for the next classes also, because this is how detailed the classes are. See, even though we take time, it's not too much time, it's not too little time. We try to explain every single thing so that no matter where the question comes from, you know the concepts. So, my dear students, I want full attendance even in the next classes. Okay, don't give up so easily because you want to become a hero. Only because of you, the series will survive. Every student comment below. And if you have forgotten to smash that like button, please like it. It will mean a lot. So yeah, almost a 5-hour marathon which we took. Bye bye. Have a great time. Take care. Good night.